Welcome to APEC. I'm Tim Ventura. I am your moderator. We're back. I have a new studio in place, so hopefully the sound quality, if nothing else, will be a little better. Welcome to everybody who is joining us on YouTube. And the Alt Propulsion channel is kind of our mainstay there, but we are live streaming across several others as well. So before we get into it today, let me go through and tell you what's going on. We're starting out with Jarod Yates doing an overview of UAP sample from the 1983 Llanilar crash in Wales. Orestis Lazanakis will be discussing additional UAP samples as well. Then David Perez and Reid Sherman will be discussing Claude's analysis of the VEM drive and Reid's work doing replication experiments. Mohammed Al-Zaraya will be discussing AI for physics engineering, and Denny Okajanani will be discussing a replication of Schauberger's repulsine. So these are all really, really exciting. I am super pumped up to be able to showcase this for you guys. And so without any further ado, I'm going to launch right into Mr. Jarod Yates. I'm going to bring him on because we have a packed schedule today. Jarod, welcome, sir.
Thank you for having me, Tim.
Yeah,
I had started sharing the tab.
Perfect. Yeah, I'm super excited about this. So yeah, take it away, sir.
All right. So thanks for tuning in, everybody. Today I'm going to be talking about one of the most famous UK UFO crash samples that are out there. Let's get into it. So just to let you know what I'm going to go over, I'm going to go over the history behind this thing. The samples are recovered after the crash, the analyses that have taken place prior to Markanize, and then I'll go into Falcon Space, Flux Space, our analysis of it. I'll focus pretty heavily on the crafts that I think this most likely came from based upon the evidence, and I'll finish it up, let you know where I stand on the whole thing. So how we start out with this whole thing. Back on Sunday, January 9th, 1983, we got a 29-year-old farmer who comes out of his house in the morning and he sees there's a bunch of metal just strewn all over his fields. There was hundreds of pieces of this stuff, and it was covering about 3 to 4 soccer fields worth of space, which would be like, 1,000 to 1,500 feet long ways. Some of these pieces were really large, twisted alloy pieces. They were painted green on one side, gray on the other, and he had like this hill on his property where he had trees on top of this, and there was a 20 to 25 foot wide swath cut through the treetops there, where something had just plowed right through and hit those trees and then distributed all this material all over his field. So he calls the police because he thinks there's been an aircraft crash of some kind. So the cops show up. Pretty soon after they show up, the Royal Air Force shows up. Pretty soon after they show up, you got the Ministry of Defense guys showing up. The Ministry of Defense guys were all wearing civilian plain clothes, not in uniform. They cordoned off the area. They worked all day, all night under floodlights. They ended up using, I believe, some heavy equipment to like scrape the soil. And like they tried to get every single bit and piece of this debris as quickly as possible. There was no report of any military or civilian aircraft that had been downed. So as far as an aircraft crash goes, nothing to go on there. After 2 weeks of wondering what's going on here, the MOD comes out and they say, it's a mystery. We haven't identified the stuff. So here's what happened was that article on this page here comes out 2 weeks after the incident, and the local MUFON guy named Gary Rowe finds out about it. And so he's on it real quick. So he goes to the farmer and they go up to that hill where the trees had been sheared off at their tops, and they start looking underneath there to see, did the MOD guys miss anything? Sure enough, they had. They uncovered these samples. You have a very large piece. I think it's the largest UFO piece in private hands at this time. You have down in the bottom center there, you can see there's a metal honeycomb looking thing that's all smushed on one side, smoothed out on one side. We also have this really thin green on one side laminate of some kind. And the very large piece has all this hexagon honeycomb stuff on there, which is really what has captured the attention of most folks involved with this, is how interesting and novel that looks. Here's a zoomed in version of it. So Gary Rowe has ended up cutting small pieces out of this and sending it to people so that it can be analyzed. And our team happened to get a hold of one of these temporarily so we could put it under our microscope and get a better look at it. Now that aluminum honeycomb looking thing on the left is from Llanilar. I couldn't help but just casually observe some coloration and wrinkle deformities that look similar to the San Agustin samples that I tested earlier last year. It seemed quite similar in some regards to that. And the San Agustin ones, at the end of the day, seemed somewhat prosaic, seemed like they were from human-made regular airplane type stuff. So the original analyses that have taken place, the first one happened in 1983. That was British Aerospace metallurgical analysis. They thought that it looked like an aluminum alloy similar to duraluminum. Duraluminum is a alloy that's commonly used on craft or on aircraft. They couldn't figure out what the green-gray coating was made of, and the alloy itself wasn't exactly duraluminum, so there was enough like tiny differences to it that they couldn't place it exactly to know it was this alloy used on this airframe. Fast forward about 40 years, and you're starting to get more stuff come out. We have 2023. This is one of the better things that came out, better research analyses that came out was from Australia team. They did scanning electron microscope and electron dispersive microscopy, and they were able to identify the elements in there a little bit better. I'll go into that on the next slide. And then we have recently Orestis, who will be presenting immediately following this presentation. I'm not going to steal thunder, so you'll have to wait for his stuff, but he identified some other elements in there that kind of match the Australia one pretty closely. And then we have one weird one-off. So it went to MUFON in Missouri in 2023, and they said from their XRF gun, they say gun, so I assume that means it's a handheld one. They said it was 94% lanthanum, which is kind of absurd. Like that doesn't make any sense for any kind of alloy or anything. They did get the iron in there at 4.6%. They did get the titanium in there, but they didn't get any magnesium. They got manganese. They did get the copper. They have no aluminum. That's the big thing that makes me suspicious about that lanthanum thing, is that everyone else is saying it's mostly aluminum, and they don't even have aluminum in their thing there. They say it's pretty much all lanthanum. So yeah, that one is weird. I've reached out to the person who did that, and I'm waiting to hear back to find out if I can get more info from that. So the Australia analysis, oh my goodness, they did so good. Casually observed that the very first thing they say is the model of equipment they use. That is basic science. That is amazing. I love that so much. The results of what they did, they did that scanning electron microscopy, the SEM and the EDX. They also tried some UV light stuff on it. They couldn't do any tensile strength, because there's some stories where like you could bend this stuff and it would snap right back. They couldn't do that because the sample size they had was too small to do that. But what they found was that it was majority aluminum. It had a little bit of titanium in it. They found that it had this graphite epoxy laminate in it, which I'll get into in a little bit. Zinc chromate would be like an anti-corrosion thing used on airframes. You also have at the bottom there an unidentified thin silicone cured resin film. That's kind of similar to what was on the San Agustin, if I recall correctly. Their conclusion was that this was definitely man-made and it was definitely terrestrial in origin. But you'll have to read the book by Mark Awley called Europe's Roswell. I showed a picture of that at the very beginning of this. He has the entire analysis in there that you can go through. This is about 25% of it. I thought this was kind of the best part, but they do go into some other good stuff there as well on the fibers and how the fibers were just starting to get used in the late 1970s in like tennis rackets. And then it went from that into like aerospace. So here's a picture from the sample that we tested under the metallurgical microscope. This is a little blob of resin that's about 0.2 millimeters wide, not very big, but it was pretty apparent right away as we saw it. Yeah, this looks like an epoxy. This looks like resin. There was these weird fibers that were sticking out from a lot of different places on the thing. And our first thought was these kind of look like fiberglass, and we're like, well, maybe it's like polyester. We weren't quite able to identify them, other than these fibers did not seem like fiber optics. They seemed like structural fibers, because in the cracks, you would see these things going across there, and they were of some differing thicknesses and lengths. And yeah, everything about it just screamed polyester to me. Here's another image of these fibers. So you can see in the upper left there, again, that's from Mark Ollie's book. You can see some of the fibers sticking out from the bottom there. I was not able to get the scale for that green image that we took, but you can see how the top of the fiber sticking off the top of the thing is kind of melted and bent over into a hook shape. And then a couple more pictures of the fibers. Here's the thing that got me all excited right off the bat, was here's just one of those honeycomb cells zoomed way in. And you can see these strange wedge-shaped things in there. If you look at the top center of the cell, you can see that that wedge at the tip, at the apex of that wedge, it feeds into a teardrop shape. And I got really excited for reasons I'll say at the very end of this, but that is very reminiscent shape of something called a slot antenna, but I don't think that's the case. Here I took some measurements so that you could see. So these are in millimeters. So the total length of the unit cell, the hexagon, is about 2.5 millimeters. The length of each of these arms of the wedges is right about 0.5 millimeter. And then number 5 there, that is the distance between the tips of those arms of a wedge, which was right about 1/5 of a millimeter. Here's a zoomed in metallurgical image of these. Apologies for some of the blurriness, but that's what you get. You can make out that, yeah, they come to a point and it looks kind of like they're molded in there, not etched in there. Here's another image from Mark Ollie's book where you can see what they called spider latches or mesh. This is the thing that I was getting really excited about initially, was terahertz. So those shapes reminded me of one of these things called a slot antenna or a Vivaldi antenna. And these come in a lot of different shapes and sizes and forms. In this particular instance, I was thinking that it could be this, but I definitely do not believe that to be the case for a number of reasons that I'm not going to get into. So going over some stealth aircraft here, because some of these hexagon shapes are very reminiscent of stealth aircraft. So one stealth aircraft that was around and flying around that time, back in the early 80s, was called Tacit Blue. This was Northrop Grumman's attempt at a stealth aircraft that didn't have a lot of faceted flat sides like the F-117. This one first flew the year prior to the event, the Llanilar event of 83. This first flew in 82. There was only one of these ever built. And it's sitting in a museum in Ohio right now with no evidence that it ever crashed. And as far as we can tell, it never left the testing range. The F-117 Nighthawk, however, has a lot of interesting overlaps going on here. So it was super, super secret. They didn't even acknowledge this thing existed until 7 years after its first production flight. So this thing had a 43-foot wingspan, about twice the width of the treetops that had been cut. It has about a dozen of them were operational and flying at the time of this event. And the leading edge of this thing, the link for that glass fiber hex cell, I'm going to upload this thing and you'll all be able to follow the links here. The link to that paper for the glass fiber hex cells is one of the best smoking guns that I've found to lend credence to the idea that maybe the stuff that we're looking at could have potentially come from a stealth aircraft like the 117. If you want to learn more about the F-117, this guy was the chief test pilot for the F-117s, and he has a lot of great stories in this half-hour video compilation he put together. One of the things that I took away from that was that the F-117 only had a 1,000-mile range, and you'd have to refuel it. And this is during the height of when they're trying to keep it super duper secret. So they're not going to be flying it all over the place where it might get picked up accidentally. They're only going to fly it when they have to. So what he said was they would develop these things at the Skunk Works plant in California, and then they would take the wings off, load it up into a C5, and then fly it to wherever they were going to test it. Normally, they were doing a lot of these tests over the Nevada test site, but they could have also just as easily flown it in with all the other C5s that were flying in to the different bases around the UK at the time. And there's a couple of bases in particular that would have made the most sense were they to transport some of these over to the UK for testing at the radar test facilities and low terrain test facilities available over in the UK. Speaking of those facilities, the image on the right here, you can see those yellow dots and orange dots. That is called the LFA-7. I believe that's the low flight altitude test range. It's got a bunch of valleys and hills and stuff. And the idea is that fighter aircraft, one of the things in their toolkit is they have to be able to fly really close to the ground really fast, because that's a good way to evade radar. So if you've ever watched Top Gun, that's a great movie for showing off that terrain following, terrain matching stuff. Anyways, if you look at the bottom of that picture, you can see where Llanilar sits, and the scale bar of 2 miles shows you that, yeah, we're just a few miles away from one of the main low flight altitude, low flight test areas in that neck of the woods. Also, just to the south of Llanilar is an MOD facility that is a big radar testing facility. So we're right smack dab in the middle of an area of the world where if you were going to be testing a stealth aircraft at low altitude, this is where you would do it. If we were to compare the F-117 versus Tacit Blue, I think that it presents a pretty good, decent argument that if it was going to be a stealth aircraft, it was more likely to be the 117. Reasons being that the 117 was flying in 81. It had already been flying for a little bit longer. It was a stealth strike aircraft. It was a fighter aircraft. And so it was doing low-level flight. That was something in its toolkit. The Tacit Blue was supposed to be a surveillance aircraft, not flying low. It was surveilling. It was flying high. For the tree strike scenario, it makes a little less sense why the Tacit Blue may have been able to hit trees and continue flying, because it was smaller. It had less footprint, and I've already gone over, there was only one of them. Versus of the 12, one of them for the F-117s plausibly could have clipped the trees and shed the material. Something worth mentioning here, if you math it out, the length of those 3 to 4 fields would be approximately like 1,300 to 1,600 feet long. And the height difference for the area where these trees would have been would be in the ballpark of 100 to 300 feet difference in elevation. So when you math that out and you're going, well, how fast would this thing have had to be going for it to distribute all of this material over that length of space? You come out with numbers between 200 to 450 knots, which 550 knots being the top speed for the F-117 and 300 knots being the average speed, 300 to 350 being the average speed when you're doing terrain following. It puts us right smack in there for the distribution length of this debris versus the height of the trees and the speed of the craft. Also, how could this thing keep flying if it had lost that much material? I will casually observe that the F-15 imaged on the left there was able to fly back with just one wing. Now, the Wobbly Goblin nickname for the F-117 was well earned. It was not necessarily the most stable aircraft, especially in those early days, especially when it was flying at low altitude, because they would turn off the automatic flight stabilizers at low altitudes. Nevertheless, this is what we have to go on. It seems as though American fighter aircraft are just built different. And who knows, if you had the right pilot in there and it got struck in the right way, the thing could have plausibly survived and flown back to one of the bases that I'll show on the next slide. The biggest weakness, though, that I still have in all of this argument is that I cannot attain any documentation that definitively puts the super top secret stealth aircraft in 1983 in UK, in Wales. There's no decent documentation that says we had these aircraft there, and we were testing them in this test range. It all has to be inductive reasoning, which it is definitely not the strongest of arguments. I will completely concede. But it's the best that I have to go on for now. So here's the basis that it seems as though it was going to. This is if it had hit there, which of the three, which of the bases had the proper runway lengths, the proper facilities to receive it. Lakenheath would have made the most sense to me because that's a U.S. base in my mind. Mildenhall, though, had some Lockheed stuff going on there since World War II, so that one actually makes a lot of sense from a Lockheed perspective. Fairford, even though it's the closest one, and Fairford makes the most sense because it's the closest one, but they would have had to very quickly moved it from Fairford to one of the other ones. So that one, they would have had to move fast because they're trying their darndest to keep this a secret. So there's still, I'm not going to nix out other alternatives, though. If we go into the exotic craft category, we have flying triangles that were also spotted in the area around the same time. And these are your quintessential 300-foot wide lights on all three corners. And they're not flying hundreds of knots. They're flying like 30 miles an hour. They're just hovering there. And occasionally you had 2 of them. In one instance, you had about 8 of them. They're all showing up all over the island, but they are showing up in this window of time, which I think is worth consideration. What I'll say about this, though, is that if you look at the February 10th one at the bottom where I have an arrow pointing, that was an instance where these 2 young guys saw 8 of these things really far away, which we don't have a good size on these things, right? Because they were so far away, they were way up in the air. It's hard to say whether or not they were seeing flying triangles or were they seeing F-117s maybe. And if they were seeing F-117s, I know I'm talking about exotic, but going back to the 117s, if they saw the 117s, then that helps us narrow down. Well, maybe if they had 1 F-117 flying over there, they probably would have had more. This tells us that they could have had up to 8, if indeed we say that that was the 117s that was observed February 10th. So to bring it all together for you, tie it together, those honeycombs with a 2.5 millimeter diameter, there are instances where, depending on what you coat those with, would put them right smack dab in the radar range for radar absorbing material, RAM, that would be used on stealth aircraft, like what's in the leading edges of the F-117. The glass fibers in those hexagons, I already provided the document if anyone wants to go read it. Those are absolutely linked to the F-117. As far as how strong the case is for it being the 117, the location, having that low flight altitude place just a few miles away, and you have something clipped these trees like it was flying at low flight altitude, might suggest that it was in some way connected to that training area. The MOD Aberporth range, just to the south, about 20 clicks to the south, that being a radar range further might reinforce the idea that it was a stealth aircraft that was being tested in this low flight altitude range. And then lastly, that 20 to 25 foot wide cut in the treetops, I think that may help us narrow down on the size of the craft that hit them. Although, to be fair, maybe it was the corner of one of the large flying triangles and it was tipped at just the right angle. Without pictures of those trees, we'll never know. And since those trees were removed in December of the same year, 1983, we'll probably never know unless any pictures were ever taken, which I don't believe there were. The fact that those trees were all removed makes me wonder if maybe it was a more regular flight path and they wanted to try and make sure that that wasn't going to happen again. So my conclusion as it sits now, terrain following stealth aircraft, it flew too low, it wasn't able to dodge, it hit the trees, but there's no good chain of evidence that definitively shows that the F-117s were in the UK or Wales in 1983. There are the list of pilots that one could reach out to, but I don't think I'm going to take it that far. F-117 is a prime candidate in my book, but undisclosed stealth, the TR-3B, flying triangles, those were showing up at the time. And it was a lot of debris strewn all over that place. I don't have the exact volume of debris that was recovered. So without that, it makes it difficult to say for sure which one it was. But the speed with which the thing would have had been flying to distribute its debris over that distance, that does line up within the flight characteristics, the flight envelope of the F-117. So jury's still out. If I had to put my money on something, I'd say prosaic F-117. But I think more information is needed to be absolutely certain. Here is all the bibliography and links that I used. That tinyurl.com in the lower right, I'm going to upload all this to there. That's the main repo where I put all of our UFO samples testing. It's where our main engineering library is for all sorts of UFO materials and patents, and a whole deep rabbit hole if you ever want to get into it. There's like 20 gigs worth of stuff in there. And if you ever want to talk about UFO sample testing, like maybe if anybody has UFO samples they would like to be tested, we would love to do that free of charge, as open source and transparent as we possibly can. Go ahead and reach out to either myself or Mark or Tim, and we'll see if we can't try to make something happen.
Jarod, thank you. Thank you. Thank you. Awesome, 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 man. So I'm going to bring everybody in. We need to give you an applause. Before we do that, though, a little switcho changeo. I want to share, let me see if I can share the Flickr album that I put up for these samples. So this is, again, if you just Google Tim Ventura Flickr, and it's the Llanilar Maury Island UFO sample analysis. This is an album with close-up photos of the testing that you guys did, the analysis that you guys did. So I believe this one is the Maury Island sample, and that is slag. And then the rest of this is basically Llanilar, and you can see, I'm just going to scroll through it really quick. This is all of the work, including metallurgical microscope analysis that was done on it, at least so far. So these are the files that Mark sent over to me. I just wanted to kind of get these up there so that you guys can see them. And that way you have Jarod's presentation that is up, and you also have all of these photos as well. So,
and I made sure, Tim, to include the link to that Flickr in the lower left of that bibliography slide.
Oh, wonderful. Wonderful. Thank you, man. Thank you. Yeah. And again, this is all open source stuff, right? I mean, there's no fees or charging or anything like that. We're just putting it up there for science and to help people understand what might be going on. So let me take that out, and I'm going to bring everybody in really quick, and Orestis is going to go in just a moment. Guys, let's put our hands together and give an enormous applause to Jarod. Jarod, thank you. So Jarod put this together on the fly. That presentation, he put that together in about like a day, I think. And that was a lot of work. So thank you so much. Man.
I spent all week on it. It wasn't a day. You asked me last week at the meeting, hey, can you present at this coming weekend?
Okay.
And so I haven't slept all week. I put a ton. This is not like me just guessing. I put a ton, hundreds and hundreds of web pages, all the books, all the materials. Like, I did all the due diligence that I could possibly do on this without talking to the original farmer or Gary Rowe.
Well, thank you. Thank you so much. Again, it helps to be able to get this out. This is like the 5th or 6th sample that we've looked at so far. And it just adds to, I mean, yourself and Mark's subject matter expertise, right? You know, and so
I'm excited for Orestis's.
Yeah, well, let's go to that right now. So before we do that, let's give Jarod one more round of applause. Mr. Jarod Yates, thank you so much, sir. And yeah, it's 12:29. This is a busy day. So yeah, let me take everybody out, and I will go to Orestis.
Hello, everyone.
Orestis, welcome, sir. So you have a presentation as well. I'm going to put that up. There we go. Hexagon. Okay. And
yeah, because it's gone.
Yeah.
I don't know where it is.
So let me take myself out and take it away, sir. Thank you again.
Great, thank you. So, like Jarod said, like he must have put a lot of work on that. We had a lot of we talked a lot during this week, and I can also see that he really has done so much work in putting this little presentation together. So thank you again. Now, I have one of these fragments, the sandwich fragments, and I took them to the laboratory here in Greece, and I am about to present some of my findings, most of them, and then I can give you my honest thoughts on what I believe might be the case with this object, whatever it might be. So I called it hexagon because there is a difference between actual Roswell and the Wales Roswell in that nobody saw that thing. Nobody saw the object crashing or coming and going. So we don't know what it is or where it's gone, and or how big it was, how much damage it could sustain. So all we have is basically the story, and the story begins when a farmer here woke up one morning and found all these pieces of metal in the fields around his farm. He called the police, believing there was a plane crash. They came to investigate, and next thing we know, of course, the military was in the area and they were picking up the debris. They were doing this together with the police, and that's the first of the interesting parts, is that they seem to be overseen by some plainly clothed individuals. You know, plainly clothed individuals overseeing military and police in picking up what could be a plane crash. Like, this is one of these instances that doesn't make a lot of sense if we consider a prosaic origin. So Gary Rowe's team decided to visit the site and to go into the nearby forest, believing they could find some of the materials in there. And they did. They discovered a few pieces compared to the 4 fields and a forest's worth of leftovers that the farmer discovered. Now, together with those pieces, they also found this big corridor that was opened and was made up by broken trees and twigs. So that's probably the direction that the craft took, because you have a few pieces in the forest and this corridor, and then lots and lots of pieces in the fields next to it. So probably the craft came from the forest side and into the fields where it flew off. Now, 4 kinds of metal were discovered on the fields and in the forest. One was the sandwich pattern, the fragments with the honeycombs on one of its sides. The other was a plate that was also hexagonal, seemed to be made by hexagonal rods or pillars. And then there was a sheet metal, a plain sheet metal that was paper thin, according to the team, paper thin, and it could almost not be bent. Like you could only bend it with a lot of force. And then there was also a memory foil, apparently. The last 2 of them ring a different bell. They remind us of the Roswell incident. But now we also have the hexagons. Very interestingly, in 2023, apparently, someone was metal detecting the general Roswell area and discovered one of these honeycomb fragments. So we have evidence of similar technologies in the 2 incidents. And that opens a whole other kind of worms, as you will see later on. Now, when the authorities apparently learned of the team's discovery, they reacted very strongly. They picked up the very forest. And the reason that was given was wind damage. According to the team, they spoke to the guys doing the uprooting, and they said that this is what I have to tell you. This is what I was told to tell you. I was told to tell you that it was wind damage. So, whatever. And on the next visit of the team to the site, even the soil was being taken. Now, there was a crash of an F-117 in Russia, and there are pictures of it. It is small compared to what it would take for 4 fields and a forest to be filled with debris. But then we don't know exactly how dense were these debris. so it could be. But we'll see about that later. So 3 independent sources that I know of have tested these fragments in addition to Jarod and I. One of them was an Australian lab that identified the most of the elements and materials in that sample, and that was a bare sheet of metal. It was not the honeycomb type. The honeycomb type was tested by Gary Rowe's team in some of their labs, and a few comments that were made were that no aircraft could sustain so much damage and remain airborne. But then, like Jarod showed us, we have other planes flying with 1 wing. And sure, the corridor, which was about 20 feet in width, corresponds to about the width of a wing of an F-117 or similar planes. So there's that. But again, like he said, without pictures of the corridor and without someone seeing in what angle or what kind of aircraft hit the trees, we cannot know more. Now, what's very interesting is that MUFON also did an XRF, an X-ray test, and they said it was 94% lanthanum, and they even found zirconium in there and no aluminum. That's the reverse, the upside down of what everyone else has found so far. But I would not be so quick to discard it, because we see a huge emphasis on hexagons here. And sure enough, lanthanum has a hexagonal crystal structure at room temperature. So that's just something to keep in mind until we have some more evidence for that. Speaking of evidence, Philip Mantle got a hold of one of these sandwich fragments, and then he sent it to me. This is the one. Now, the hexagons in my sample, in this little object, are different than the ones that Jarod showed you. These ones look apparently like melted or having been exposed to a high temperature. And then you have the green layer on the other side. It looks black, but it is actually dark green. And at the top, you can see one part of it was chipped away, and underneath that was a slot in the metallic regions that was seemingly made for the green layer to go into, and you can even see a right angle. So this is a very human-looking thing, but we just don't know yet. Here is a closer up of the hexagons. You can see the cracks, probably a result of Gary Rowe's attempt to crush the material. And you can even see the fibers. If you look closely at the bottom side of this of the material, you can see those weird fibers sticking out. Now, you can also see a hole, a big hole towards the left of the sample. That hole is also hexagonal. I don't have a picture, but when we were turning this object under an optical microscope and changing the perspective and the lighting, at some point, the orientation and the lighting were just right, and you could see that this hole was actually hexagonal, a smooth hexagonal hole. So even more hexagons. This is the metal that you can see. It has 2 distinct regions, a clean one and a dirty one. The dirty one is, has some dark spots, and the layer right beneath it is also very dark. And so one could say that the cutting tool dragged some of the material onto the metal. But from observing this third layer, it looks very brittle. Like, I don't think that this layer could have been sort of applied like stick to the metal by the cutting instrument. I just don't know. Here we can also see that this thin layer used to be part of a thicker layer, or maybe there was a sub-layer underneath it. As you can see, it snapped, probably during the crash or the hitting. I took these samples to the National Center for Scientific Research, Demokritos, in Athens, Greece, for scanning electron microscopy and EDS, elemental analysis. And I also cut a smaller piece and exposed the insides of each layer to have a better view of it, to be able to more or less measure the size, the thickness of each layer, and to have an uncontaminated part that we can compare against the other EDS spectra that we would take. This is the first one. This is showing the gray layer. As you can see, the hexagons. There is also a part of it that is broken off, peeled off, and you can see the inside of the layer. It is very porous. And this will become relevant later, because as we will see, a lot of stealth materials are sandwiched, lightweight, porous. And curiously, this layer is also made mostly out of aluminum. Even though it's gray, still a lot of aluminum. So it's probably doped. Maybe it's a resin or a ceramic of some kind. And here you can see the hexagonal hole. And I positioned it so that we could test the inside, and on the inside of that hole, we could find some elements that were not present in the rest of the layer. Sodium and chlorine were found, so salt of some kind if they are bonded together, which is interesting. Could be rainfall, could be anything, but there's that. Like we don't find some of these elements on the rest of the layer. And here is one of those fibers that was sticking out. Now, this is only what's left of it. When we first found it with the electron beam, it was much more textured and detailed. It had all these hooks and branches and things sticking out of it. But when we zoomed in, it shrunk a little. So we just stopped immediately and zoomed out. So maybe the electron beam destroyed some of its features, but you can still see them. You can still see them, and it is coming out of the layer. It's not between. It is not sandwiched between the metal and the gray layer. It's actually coming from holes from inside the gray layer, which is interesting. And it also has a lot of aluminum and iron, enough for the scanning electron microscope to detect it. So these are weird, these fibers. I don't know if a stealth application could be for them, but that's what we see. And this is the metal up close. You can see the two regions. The dirty region is the one to the left. You can see the spectra. And the cleaner region to the right does not have all these other elements that will also be detected on the thinner layer. And here is the clean, uncontaminated part of the small piece that I cut, showing even fewer elements, mostly aluminum, not lanthanum, not zirconium. We will have to see. Maybe we should do an even more sensitive test to settle the issue once and for all. If, at least in this sample, we could find any lanthanum or zirconium. We'll see. And this is the third layer, the thinner one. This is, I believe, the most interesting one, because this is very thin, but it has all these different elements. At the top spectrum of the EDS, you have the layer when viewed from perpendicular from you, and the second spectra is from the clean part. There is not a big difference between the two. So this third layer contains so many different materials. You have manganese, you have lead, you have aluminum, we have chromium. We have all these different elements that we don't find in the other ones. I actually see a difference of density progressing inwards towards the thinner layer. So the outer layer is one of the thickest ones. It has a lot of aluminum, but also some other lighter materials. Then if we move inwards, we have basically mostly aluminum, so denser. And after this denser layer is an even denser layer, this third thin layer with all these elements that are denser than aluminum. So density increases as we go inwards, for whatever that's worth. So this is probably what happened. Maybe maybe an unknown aircraft, was flying low, hit the trees, but then it kept going and scattered all this debris on the field, and it was discovered the next day. Now, the kind of worms that I was talking about earlier, we have so much material reportedly found in these fields, yet not a single mechanical or functional part. No engines, no wires, no nothing, not even bolts or rivets. Like, if such a big chunk of a human craft was scattered on a field, you would expect to find one bolt, one rivet, something, or a plate with holes for these rivets. But we do not find any such thing. Where we do find something obviously human is in the newspaper article. The newspaper article claims that one of the pieces had a serial number on it. But when Gary's team asked the farmer about that, the farmer said this was not the case. So, the first time the world hears about this incident is from that newspaper article. And Gary's team arrives after the fact. And after their search, then the authorities decide to uproot the forest. So if they scattered these pieces at the site to be found later, why would they take the forest and the soil to remove all evidence? So, and then what about the Roswell type materials? We have a memory foil. We have this sheet of metal that was also found in Roswell. And now the hexagons apparently as well. This is a big problem to be solved, in the ufological world, because if this is a stealth human craft, then what about Roswell? Why do we find the same elements in Roswell and San Augustine, perhaps? And if it is an NHI, then why do we find so much evidence of human-built stealth materials? Lightweight, sandwiched, metal cores, foamy materials, hexagon. Even the hexagons have many applications in radar absorption. And like Jarod said, the diameter of the hexagons is just right to absorb, to be tuned actually to radar frequencies. Now that just means that the maker wanted to have a stealth craft. That doesn't tell us anything about the maker himself or herself. What may tell us more about them is if we do an isotope test. Like, we really need to do that, because if we have two possible sources, a human one and a non-human one, if we have possible human craft and exotic craft at the same time, we need to know what the thing was, because it is directly related to Roswell. Like, I don't know, maybe an F-117 collided with a UFO. That would explain things. We just don't know yet. This is the end of my presentation. This research is ongoing, and I'm just not jumping into any conclusion for either for or against a UFO origin. We'll just have to wait and see.
Orestis, thank you, man. Thank you so much. You guys are blowing it away. Let me do this before anything else. Again, I'm going to bring everybody in. Please put your hands together for Mr. Orestis Lazanakis. So you guys double teamed this. Thank you so much. It's wonderful to be able to showcase the Llanilar sample in more detail and go through some of the different possibilities that may explain it. So we've got about 10 minutes. Do you guys want to do open discussion? Does anybody have? Mikolaj, go for it.
I was just questioning how difficult is to do the isotopic analysis, because that's what I would have started. I mean, Orestis, I agree with you. This is the main thing. But is it difficult? I don't know.
Well, recently I found a laboratory here in Athens that can do it. I have done it for other samples that I have presented in a previous episode here. So this is the next step. No, it's not difficult. It's just, it's just more expensive So naturally, since we pay for all these tests, it will have to wait. But it is definitely happening in the next few months. I definitely want to find more evidence to because I want the evidence to take us to a conclusion. I don't want to give a conclusion before the evidence.
But don't you
So
think this
definitely.
should be the first thing to do? Because otherwise, it's a waste of time if it's Earth, unless the aliens are making stuff on Earth.
Yes, I see what you mean. And no, this is not the case. You need to identify the materials first in order for the machine to know and the operator to know what he's looking at. Like, you cannot just put one object in the isotopes and get all the isotopes back. You will get all sorts of interference and noise. You first need to do some preliminary test to see what elements you're looking at. And then, armed with this knowledge, the next operator will be able to use their instrument to zero in on the isotopes. You have to do it, step by step.
Thank you. That was a
And
great answer.
If I could just add one other thing to that, assuming that it was made on Earth as being something that means that it's no longer valid for useful engineerable insights, that might not be the best path forward, right? Perhaps it's still possible that some of these craft that are flying around, they could be ultra terrestrial, they could be time travel. There's lots of weird stuff out there on how this craft could be terrestrial isotopes and still really interesting. Even if you want to go in between the crazy and the prosaic, you could have humans in the 50s, 60s, 80s. Maybe somebody somewhere built something really cool and it crashed, and we get a piece of that. By looking at that thing, assuming it's not part of something that shouldn't be disclosed, like stealth tech, something that should be disclosed, like cool propulsion tech for the Alt Propulsion Conference, that would be an instance where I would say that the isotope tests showing it as being terrestrial and even a recent terrestrial might not necessarily be a deal breaker.
You mean reverse engineered stuff?
Yeah, so if humans reverse engineered something and built their own and then crashed it, and we get a piece of the crashed one, I still want to look at that.
Absolutely. Exactly. Even if this is an experimental craft, then that's even better if you ask me, because we can reproduce this thing. We can actually, get to know what they were trying to build and why it crashed.
Well, one of the thoughts that has kind of occurred to me, and again, this is the 5th or 6th different sample that you guys have done analysis on. And then Orestis, I know that you have looked at several implant samples as well. And for me, my mind goes to this idea of developing subject matter expertise. I mean, this is beyond a niche skill set, right? You are a couple of the only people in the world that have done this research. And in terms of like the scope of samples and the diversity of samples and their origins, I mean, that is beyond compare. So we can't control really what the material is, and we can't control where it comes from, right? I mean, we can make sure that we verify, yes, this is from an actual reported crash, but you can't control, was that a stealth fighter or was that, little gray men out for a joyride in a UFO? And so my mind goes to this idea of, practice makes perfect. And the more of these that you guys are able to do, and I would love to have more reporting on this, right? Whenever you guys are able to bring stuff like this forward and describe it, I think that is incredibly valuable, even if it is just a piece from a stealth aircraft, even if that's what it ends up being.
And one more thing, remember that things change, and tomorrow another craft may crash. What if we find the same kind, of metal in it, but now we have witness testimony to tell us if it was little green men or gray? That would change a lot of things, and we would already have some research to back up the next one.
Yeah, no, that's a good point. Well, and speaking of things changing, I was just looking at and this might be something we get into later, but I was looking at the president unsealed records, the UFO records. And one of the things that jumped out at me were you've got photos of the UFOs by the astronauts on the moon, right? I mean, So it's these little bits and pieces that add up to big changes over time. Well, does anybody else have any questions? Yeah, Drew, go for it, sir. You're okay. There we go.
Okay, it looks like, and I'm sure that was AI generated fields and stuff, and they were taking away a forest. What's the rational thought for digging up a forest and then the dirt 2, 3, 4, 5, 6 feet down? How do you? I mean, that's not a trivial task. You're lifting up a couple of 100 acres of forest, and then what do you do with a couple of cubic miles of soil? Do you build a big dump somewhere? I mean, that dirt went somewhere. They didn't eat it. I mean, is somewhere there's a new mountain in
The
that
White House, the
soil?
White House garden. It goes to the White House garden. That's where
Whatever.
all of the UFO parts and wreckage are buried.
I mean, you look at a dump, you can see a volume of a cubic mile. That's a forest.
They are close to the ocean.
You dumped a forest in the ocean?
It's a good place for dirt.
Okay. It's gonna
Well-
wash up on the beach.
Well, since you asked, it was wind damage. Like, if wind blows, now we have to uproot a forest. Okay.
I have a question.
Okay.
Was there any radiation detected in the samples at all? Did anybody analyze
Not
for
yet.
radiation?
Not me.
We did not have time to do a radiation test. We had about 40 minutes with the sample, which was just long enough to get pictures under the microscope, unfortunately. If we get it back, I'm going to try to do more testing with trifield meters and resistances and conductivities and capacitances and, all electrical characteristics of it. But yeah, no radiological tests done on it, unfortunately, for the one we had. And I didn't find anything in any of the literature that suggested they'd done any radioactive testing on it.
Because that would be a good reason to remove soil if the metal actually contaminated the soil so that the farmer couldn't have a pasture or the trees would be contaminated. That would be the only other reason why you would remove that.
Consider that the big piece, Gary Rowe has been cutting off small sizes like the one that we showed. He's been cutting off pieces like that and putting them in keychains and selling them for 20, 25 bucks for the last 40 years. So if somebody would have gotten sick by having one of these things in a plastic keychain that they're keeping in their pocket all the time, I'd have to imagine if it was that radioactive that somebody at some point would have said, why is my hair falling?
Wait,
Wait,
what?
could we
He's
test the
making
keychain, though?
Yep. Yep.
What? I'm
20
confused.
pounds.
So he went and scooped up a whole bunch of stuff before they came and dug the forest up? Okay.
Yeah.
And they made keychains out of it.
Yep.
Can we get one of the keychains?
I don't know. I don't think so anymore. Like, maybe.
Maybe. Yeah.
This is awesome.
Well, guys, we're at the top of the hour. Let's do this. Let's put our hands together one more time for Orestis Lazanakis and for Jarod Yates. Both of them knocked it out of the park. Amazing presentations. And now let me take everybody out and we're going to go to Reid Sherman. So Reid, let me see. Welcome, sir. Okay.
Thank
sorry
you.
about that.
Can you hear me okay?
Yeah, so this is the first time you have been on the APEC conference. You have been doing replication work on David Perez VEM Drive. And
Yes.
from what I understand, you've had some really exciting results. So you mentioned doing screen share, I think. If you press
Yes. Let me do that.
yes, the plus button and then share screen. And that's the safest way if you want to do videos and stuff. Again, we're using StreamYard and it gets a little cranky with, like, it won't allow embedded videos. It has some quirks.
Okay. Okay. Here, I'm just going to do share the screen. All right. Yeah.
There we
You
go.
see it okay?
Yep.
All right.
Perfect. Okay.
Awesome. Very
Wonderful. Okay.
All
Well,
right.
thank you so much. So I will take myself
you for
out. I
having
will
me.
be here if you need me. And yeah, take it away, sir.
good. Awesome. Thank you so much. Well, hello, everyone. And thank you for having me at APEC. This is my first time here. My name is Reid Sherman, and I am a NASA Nebraska student fellow working out of the University of Nebraska-Lincoln. So for the past year, my research has focused on testing the variable electromagnetic propulsion system, called the VEM Drive for short. Since this is the Alternative Propulsion Engineering Conference, I think most of us already understand the basics problem with rockets. Rockets work extremely well, but they require a huge amount of propellant. That makes deep space missions difficult, expensive, and limited. So if we want to take humans to deep space, build a real space economy, and eventually move beyond the inner solar system, then we need to explore propulsion systems that do not rely on conventional chemical propulsion. So that is what led me to David Paris's work on the variable electromagnetic system. The basic concept behind the VEM drive comes from the electromagnetic conditions that may occur during high energy thunderstorms. In these environments, unusual effects have been observed that suggest possible local distortions in space-time. So David Paris, the founder of quantum electrodynamics, worked to recreate those electromagnetic conditions in a laboratory setting. Using interferometer-based experiments, he was able to measure that there was a distortion in the fabric of space because of the laser's beam was actually getting shifted in its wavelength. So thunderstorms create distortions in space-time. Great. How does that help us? Well, the next question is whether this effect could be used as a propulsion system. The VEM drive is designed to create these electromagnetic conditions and produce a compression field in space-time. The goal is to create a pulling force without using conventional reaction mass like chemical fuel. And right here we have a picture of the fractals arranged in the VEM drive. And what this does is this is supposed to replicate the crossing fields of a thunderstorm to generate that compression in space-time. Right here we have a video from December 15th, 2023, showing Model 19 doing a 1500 watt test. If you're good with that, I'm going to play that right now. I'm going to just kind of skip ahead. There's no audio in this example, so I'm just going to kind of go through. You can watch the whole YouTube video yourself, but as you can see, there is 1500 watts and 30-second test interval. And here's the video in real time of the dial being pushed down of the VEM is being suspended from the roof and it's just pulling straight down. So my whole research is basically to see, can I replicate this? Because, you know, the mark of good science is it's not something that you do by yourself. If you can repeat it and you can do it, you know, no matter where, then it's like, oh, this is something that is like really groundbreaking. Sorry, I just love watching this video because this video shows just how strong the VEM system can be, especially in real time. I mean, this is absolutely insane that this is happening due to just a compression on the fabric of space. So kind of exiting that video. Oh, present. One of the fun things is that during testing, quantum electrodynamics reported the system producing a pulling force of over 15 newtons. That is 3 times larger result compared to NASA's latest Hall thruster, the X3. And the VEM drive can do that at 1.5 kilowatts. Once again, compared to the 100 kilowatts that it takes NASA's X3 to produce its maximum thrust. So I just made this funny little graph here just because it shows the absolute insanity of the difference here between the efficiency of the quantum electrodynamics VEM drive and the Hall engine. I absolutely love this. It's insane. So my job was not to prove the entire theory in one step. My job was to ask a simpler question. Can this effect be reproduced independently? That question matters because science has to be repeatable. If a result cannot be reproduced, then it cannot become a reliable engineering system. So I reached out to David Paris and proposed an external verification project. I wanted to build and test an independent VEM system and see whether I could reproduce the reported effects. After a year of work, I was able to reproduce repeatable directional movement using my own VEM Drive test setup. As you can see in the top left corner, I have just made a little diagram, kind of what's going on there. My artistic skills, they're wonderful. The biggest milestone happened on January 11th when I completed 10 successful tests. This was important because one of my biggest concerns was that this effect might be like catching lightning in a bottle. Maybe it was something that could happen once or twice, but not something that could be controlled or repeated. The 10 successful tests in a row showed that this effect can be repeatable under controlled conditions. So at this point, I wanted to show a few videos from the testing. The first video in the bottom left corner shows that the kind of the weakness of my first mounting setup, but it did show a actual movement being generated. Goodness. Sorry, Canva's wonderful to work with sometimes. Gosh. As you can see the video, this is sped up to 2 times speed, just showing that there was a rotation moment created around the mounting mechanism because it was a poor nylon string. But that was my first successful test showing an actual compression being generated. On this next video that's already playing, this is a video of one of the 10 successful tests. I believe this is actually our first one. And as you can see, the dial is actually moving from right to left because I did not get the focal point perfectly managed on this one. So instead of creating a perfect pulling force down, it just started going. But as you can see, there was a slight hiccup in the dial. This is real time. As you can see, there's the power going in and then the power, and then there's no reflected power coming back. This video is also really interesting because it shows like how much electromagnetic frequency is in the air, even with the Faraday cage. Unfortunately for this experiment, when we had the actual power go into the system, the view, the expanded view, actually that camera freezes because of how much electromagnetic frequency is in the air. So as you can see, the motor's now moving, but the camera is still frozen, and it's going to be frozen pretty much until power is cut. And then the power cut, and then there goes the camera back. So, you know, it's been a really fun experiment to get to work on this. But even with those issues, the most important point is that the movement was repeatedly generated under similar test conditions. Basically, to recap, I was able to independently reproduce the repeatable directional movement using the VEM Drive system. I think there's still a lot of work to do. Kind of the next step is to improve the testing setup so that the results can be measured more accurately and with fewer possible sources of error. My future work will include a larger and more stable test rig, stronger PCB fractal arrays, and a multi-point interferometer setup, so I can measure the field at different locations. And kind of the goal is to keep improving the experiment until we can clearly see the VEM's effect on the fabric of space and to better understand how to improve on and design a better device. This project would not have been possible without the support of David Paris, Kyle Finley, quantum electrodynamics as a whole. I would also like to thank Dr. Baisui and Luke Wadley at the University of Nebraska-Lincoln, and of course, NASA Nebraska Space Grant for, giving me the ability to facilitate all of this. This has just been a wonderful research I've been able to get to do over the past year. And yeah, I'm really looking forward to continuing this work. Thank you so much.
Reid, thank you, man. Thank you so much. So yeah, quick walkthrough, but incredible material. Thank you for presenting that. Let me bring everybody in really quick. And I know David is going to do a presentation also, but before that, Guys, let's put our hands together for Mr. Reid Sherman. Reid, it was wonderful having you present on that, and amazing. It's amazing to see validation for the work that David has been working so hard on. So
Yes.
thank you, man.
Yeah. No, I'm open to questions. Anyone has anything? I kind of went through that quickly. Yes, Nikolai.
Okay, maybe I didn't understand your setup, but here what I see. You have this thing, okay, and you have lasers on top of that. Two things. The lasers would ionize the air. The air would push on this little doodad, okay? Then your Faraday cage insulates from electrical field, has no insulation of magnetic field. So have you taken these things into account? That's all. Or maybe I didn't understand your setup correctly.
I did not take into account the magnetism. That's one thing I do have to keep into consideration. Kind of because of the setup of that experiment. You're right entirely about the ionizing part. That's why I was thinking that it would be best to do in a more crude vacuum chamber, like not to get the atmosphere basically down to 0.1%, just so that way it reduces the chance of ionizing. The real goal is to measure where the lasers are shifting in their wavelengths, because then it's like, hopefully with that setup, I can then see the specific points of where the structure of the compression is actually happening, and see if that mirrors what Dave Parrish is going to be talking about later, which is what he was using. Is he's been doing mathematical descriptions of those compression fields. So I just want to see if experimental results match computational results.
All right, good luck with your new setups with the vacuum chamber and stuff like that. But I think without a vacuum chamber, I think it's fairly, you're open up yourself to criticisms and stuff like that. So easy.
Unfortunately, yes.
Good luck.
So I guess the question that I would have is, Reid, from everything that you've presented, it seems like you are incredibly optimistic about this project. I mean, is this one of the ones for folks who are out there looking for things that they should be focusing on? Is the VEM drive one of those? Is this on your short list?
I think so, because it is, like, I've seen it move. You have video evidence. I mean, it's been incredible. The amount of efficiency, like I showed right there, even though that's kind of a ridiculous, example, because what that is, the actual efficiency for the newtons produced per kilowatt is incredible. So, I think that's going to be huge. If humans want to become an interplanetary species, I think that is the first thing that needs to be taken care of, is propulsion. That was actually one of the reasons I joined the project, was because I knew that was like the biggest issue. I wanted to create a space-dependent economy, and to do that, the propulsion question has to be solved. Because you cannot do anything in space if it takes 6 months to send a rescue team to Mars, or really it's going to be 2 years, because when something bad's going to happen, it's going to be when Mars is as far away from Earth as possible. So, to be able to get a crew to, be saved or rescued or really do anything in space, I think that those travel times need to be cut down drastically. And
I have another question.
Yeah,
sorry. Theoretical question. How do you deal with Lorentz invariance in the theory? Yeah.
So that would be a question better directed to Dave, because he's the math guy and the experiment guy. Yeah, I think with the future of space travel, having the best propulsion system is key. And I think this is the most tangible propulsion system that we have right now that can deliver that future.
One of the things that excites me is just you're getting involved and having some independent validation of David's work, right? The more people who are getting involved, seeing results, documenting results, seeing his work in the lab, the better it is, And so I think, it's like the rising tide that lifts all ships.
Yeah, exactly. Yeah.
Okay.
That's true.
Hey, Reid, did you build the thing yourself, or did you get that from Dave, or?
So let's see. The fractal designs were given to me by Sir Dave. I also did the testing there, but Sir Dave didn't really facilitate like that. Like, I did it there because he has the licenses to do that work there. The lab I was working at didn't have the right licenses needed to work with radio frequencies, because the United States government doesn't like people playing with, just random radio frequencies, because that can cause all sorts of issues. So because the facilities are already made at QED, I facilitated some of those experiments there. Now, of course, the scope and design of that was decided by me. So, yeah.
Thank you.
No, thank you.
Yeah, absolutely. Well, guys, let's put our hands together one more time for Reid Sherman. And then I'm going to go to David Perez. David, thank you, sir. Let me take everybody out except for you. And so you are going to do a screen share as well, I think. This
Yes.
might take us a moment to get there. If you click the plus button,
Right.
and then it should be just share screen. And then it will pop up a little window. It has Chrome tab, window, or entire screen. And it should have a little slider that says also share system audio if you're playing videos like that.
I don't, the videos don't have any audio.
Okay.
Okay.
Yeah, so again, it's that plus button and then share screen. And every now and then Chrome runs into permissions issues. So I'm crossing my fingers, but.
Okay. Where are we going here? Huh. It worked great for Reid. Why not me?
Yeah, it's a little bit different than Zoom. What StreamYard leverages built-in capabilities that Chrome has. There we go. Looks like, yeah, okay. There we go. It's coming up.
Whoa.
Yep, and it's showing your entire screen, sir. So if you go over to whatever the window, so it's your browser is maximized.
Yeah.
So if you bring up whatever window.
Oh boy. Okay. Oh man. This is let's try it again.
Yeah, no worries. No worries. It's computer land.
I'm just QED. About the window. Here we go. Okay. I think we got it.
There we go. Perfect. Perfect. There's your PowerPoint, sir.
All righty.
Okay. So I will take myself out. And again, I will be here if you need me. And just let me know. But thank you again.
Okay. Well, I'm going to start the slideshow here, and we'll get into it. I've been doing a lot of work with Claude AI, and it's been very fascinating. And I've written 9 different software packages that pertain to our project, the VEM Drive. And the goals is to, like what Reid was talking about, was to become a space-based economy, retrofit satellites, station keeping, moving materials to space, launch without booster rockets, travel faster than light, which is all very possible. The AI, I put this in here because I kind of, it's always been hard to describe. People ask you, well, how did you really come up with all this? And the critical part was, I'm a meteorologist, physicist, astronomer. I teach all those subjects at college. And I'm an engineer, scientist, and I've been with the research labs, Battelle Memorial Lab in the Army Atmospheric Science Laboratory. But I really come from an empirical background, observing and then testing and seeing how it works. So the description that I didn't have any input for Claude came up with this. And I thought that was kind of fascinating that after going through all the data and all the papers and everything else that I've done, that it came up with this conclusion that he comes from atmospheric physics, not theoretical physics. He approached the warp drive the way meteorologists approach weather, empirically looking for immeasurable field effects. And that's exactly what was going on here. Now, our drive and the way it works, we have the theoretical of Alcubierre, which has the Alcubierre metric. Compression in the front, compression in the back seems to be, if you can create that warp bubble, which was an incredible amount of power that he had predicted. And Van der Broek and Sonny White had reduced all the amount of power potential to create a warp bubble. But they were all using exotic energy. And that was antimatter, dark matter, dark energy, and all this really kind of wild stuff. And it really came down to, believe it or not, you can compress the fabric of space with 48 volt DC and several linear amplifiers. Well, the actual, when you build one of these things and you get results, it's the AI came up with this, these first bunch of slides are AI. I put in the pictures, but parametric distortion, space-time conformation, but with the key difference, compression in front, relaxed decompression in back, plus moment latency, plus movement latency when power is off. We've actually run some experiments where we videotape all of our experiments, and sometimes we're looking at something else and we let the video run. Well, on this particular occasion, it was a 300 watt run, and it was, we had 10 grams of pull on the 1 foot motor. We have 24 different engine types, and we're running one on for CubeSats. Anyway, the bottom line was we left the video running, and then we saw 15 seconds of latency of the power was off, but yet the engine was still pulling. And that that was quite of an interesting revelation, is that the engines, when the power is totally off, the fields are rebounding and going back to ground. So in this case, there's a slight reduction in the power in the back, in the pushing power. So it is not as intense as in front. And this picture is the original that we have of I'll put the cursor there. This is a depression over the tripole fields. This is a depression over the tripole fields. And then there's a null area in between the fields. This is pretty interesting stuff because we're shaping the compression of the fabric of space, but we're able to shape it. Recently, since I've been writing all this software, been able to reproduce with our relativistic space metric equation, which is the Planck's constant times the frequency of over the square root of 1 to v squared L divided by c squared. The reason why I mentioned the transverse and longitudinal pieces of that is that longitudinal waveforms will produce the greatest pull. In other words, all the magnetic, the temperature, everything else in the front of the wave on a longitudinal waveform is more powerful than a transverse wave, which it's distributed across. And what we did was, in writing the software, we put that relativistic equation in here, and we're able to reproduce the fields that these engines develop. And we've engineered it so that we can even see the fractal design and create the various iterations in the fractals. Interactively, we can take a fractal that is normally we produce a CNC fractal for 6 iterations, but in the software, we can bring it down to 1 iteration, and there's a variation in intensity of the fields that are generated. So we have now complete engineering tools to look at from our fabrication of the tripole fields, but we can also integrate in to see what a field effects are for the amount of iterations that you have in a fractal. These things are pretty interesting in by themselves. Part of the software that we use also allows us to configure these things geometrically into quad shapes, hex shapes, octagon shapes, so we can strap engines together. And what we found is that there's a coherent constructive interference, as we call it, as a CCI. And as these fields overlap each other, and we take a standard M19 engine and configure it, and this is a quad setup, and this is where we hope, oh yeah, there we go. The software will allow you to interrogate the engines. You can roll, pitch, yaw, everything about the motors in these configurations. You can adjust the fields and overlap the fields. And with a 15 Newton force on the engines, the prediction here is that we can intensify the actual pulling rate of the quad system. Now we can design by 2, 3, 4, all the way to 10. And the amount of lift capacity on a octagon of these M19 engines is pretty incredible, which means that you could lift material and go to space without a booster. And that's what we're working on right now, is the next gen of a lifter. And this is all due to the software that's been developed. And the real bottom line here is that we also have this AI software being developed to hook directly to the engines to control them. So we have a whole software package of initiator that will start the engine, build the field, do all the characteristics that have to be done that we do manually right now, but will be monitored totally by the AI software. So this is a huge this is a huge advancement for us in this next generation that we have. We've already proven that it pulls, it works, wherever direction you put the engine, it goes. Now it's a question of how much power can we put into this thing, and how it can, as an aggregate, force it, in this case, overlap in the fields to generate even more pull on the engine to lift things up off the ground. So one of the things that we have in the confirmation of the system of that we're compressing the fabric of space is we experience redshift in the engine itself. And this is a frequency redshift and blue shift in the back of the engine. So it's pulling and pushing. Now, part of the thing that makes this all happen is, as we discovered here and investigating with Claude, is we inadvertently have come across a macabric symmetry where the fractals themselves, which is this one here, one placed up and the other one inverted, forms a gradient. And what's interesting here is that the fractals themselves, unlike a string or a wire, it radiates everything outwardly. However, when you use these modified Koch curves, which I designed, you're basically taking the equivalence of like a 12-foot antenna that represents the frequency that we use, that represents the freezing level of a thunderstorm, that these nested current loops occur as a result of the iterations that are on these fractals here. So this is a 6-iterated fractal. And as the current flows into the engine, it creates these nested loops. And the fact that they're inverted to each other is another factor that creates a longitudinal compression. So we actually literally, in the engine itself, due to the fractals that represent not only thunderstorms, but reduces the overall aggregate length of an antenna. These are antenna arrays, but they don't act like normal antenna arrays. And what they do is they radiate. They don't radiate an RF signal, but what they do is they create a structure, reactive field compression. And this is what really drives the engine. And when you overlap those fields, you can magnify up to 50 times the input power from one engine. And with multiple engines, when they overlap, can actually amplify that power, that coherent constructive interference. And this is what makes the VEM drive really remarkable, in the sense that it doesn't require a lot of power. It doesn't. 1500 watts is the beginnings of when things begin to get interesting. You can get results at lower power levels, like Reid did, and he did those lower power levels because those were CubeSat style engines. And they're the least potential of creating any kind of harm. Now, we've tested our engines, and they don't have any effect on humans at all, in the sense of the power that comes out of these things. We've measured the radiation that's emitted. It's 1.5 microrads at 3,000 watts of power. So it's nothing. But we don't have we don't have insurance and stuff. So when somebody comes into our lab, you're talking liability issues. So he worked with the low powered stuff, and which is benign. So we know that for a fact, but we didn't want them working with the high power stuff like we do. We've been doing it for 15 years, and we're still here. Anyway, that's kind of a diverting off the side here. But the openings of the engine are critical. The actual engagement of the engines are critical. You have to create a field. You can't just flip it on and all of a sudden something happens. There is an entire process, a cycle that goes on depending upon the type of materials that you're using in the VEM drive. If it's aluminum, copper, silver, or whatever you're using as the fractal base material, each one has a different characteristics, which then initiates a different initiator for activating the engines. So we've learned a lot. I mean, it's pretty interesting stuff. It's taken a very long time to come up with not just explanations of it, but the building of these engines, getting them fabricated has been a problem. Going to different machine shops and getting stuff CNC'd out. We've encountered all kinds of stuff like that, but we've overcome it. But this is the future right here. Now Reid was showing you the baby ones, but these, the 2-foot models, the M19s, this is the real future of not just QED, but the future of space travel, is to mount these up into different geometric configurations. So there's no propellant, runs on 48 volts DC. We have a person in Kansas City. Tim will probably have him on at another APEC conference, but he will be talking about quantum fuel cells. And they're very lightweight. They deliver a lot of power. But we only use 48 volts in our linear amplifiers, which can go up to 6,000 watts of power. And we do all of our testing low power because in space, you don't have the resources to really blast, 6,000 watts all the time. But what's also interesting about this is that conserving the power ratios is also critical. You want to get as much as you can out of as little power as possible. Plus, these curves that we've run are exponential in nature. And what they do is they, with a little bit more power, they can drag up even more weight. And if you cluster those again with additional engines, what will happen, and I'm trying to get to this one graph right here. Okay. The R square values of this is an early model 15 that we used. But the R square value on this bad boy was 0.9992. 1 is perfect. And this is the kind of curve that when you put power in, it doesn't take much more to get out more newtons of working force. So this is, again, part of the hardware that we have, the software, throttle, battery supply. Everything runs on battery. It's all 48 volt driven. There's a pi tuner in there, but the new future engines actually have the linear amplifiers onto the board itself. So there's a lot of new things coming out and things to be tested. It's kind of, that's a copper engine. This is the quad setup that shown just a little bit before. The overlay of the fields and the fields in the back of it. These all are the characteristics of a warp signature. And when you deploy these around a craft, that's exactly what will happen. You'll have compression in the front, decompression in the back. If you turn the engines off, you'll have latency, and this thing will still move forward. So there are some other issues that we have to consider here. Is before you get someplace, you're going to have to reverse your motors, or turn the rear motors on to slow you down, because you'll still keep moving forward. It's not a dead stop in space, as we've discovered into terrestrial space. As you cut power to the engine, it still moves, and there's still a latency there, which means it has momentum, which is quite unique. This is the arrays push out their energy this way. It crosses and creates a lobe and produces. This is the first, I guess, actual image of a field of a warp field signature. And what we found out was that it's not a bubble; it's a path. And this is something that's new and innovative in that regard. Everybody, the theoretical has gotten everything as a warp. It's a bubble. It's a bubble. What we've been able to figure out with our experiments and with our now our new graphics and whatnot is that it's not a bubble, it's a pathway. So it's a path that literally space goes around the path of the pathway of this compression of the fabric of space. Also, we affect gravity. With our earlier experiments, we've been able to produce different gravitational effects with the engine, so it does affect that. So one of the ideas that we had was we could create artificial gravity inside of a spacecraft. You can build warp bubbles within warp bubbles. I've already done that in the lab years ago. And turning characteristics, control, and all this type of thing. One of the other interesting characteristics of the motor is that engine sitting here with the thermal infrared camera, and then after it, we can cool the ambient air temperature 4 degrees. So the ion effect and some of the other things that were discussed as far as potentials, thermal heating and all this, that doesn't play into the way the engine works. It actually does compress. We've set up blocks of with torsion bars and weights on them, and closed them into a solid structure, glass and wood, and put the unit, a small unit, like 140 centimeters away from the box, and can pull the, whether it's ferrous or non-ferrous material, and it pulls it at the same rate. Yeah, so it's not charged. It's not ion. It's not anything but compressing the fabric of space. With 2 gravity doses of 1.47 meters per second squared, you can hold an astronaut on the ground of the floorboards of a spacecraft. And we thought, wow, you can do warp bubbles within warp bubbles. Well, why not use it for artificial gravity? That'd solve a multitude of problems in space as well. And this is a prototype. It's a 7 by 7 foot prototype of the Bluebird, which we will put an engine on top of it when we're done and lift it up off the ground at the Council Bluffs Airport, which this is where the craft is sitting right now. So we have a lot of things in the fire, a lot of things in the pipe coming down. It's been a lot of work and it's been a lot of fun. And we keep pushing forward. And that's it.
David, thank you so much. Thank you, man. That is amazing. You guys are all hitting it out of the park today. I am overjoyed. And I'm going to be cutting these up actually and putting them up as single shows also and promoting them on the alt propulsion side just to make sure that they get all of the attention that they absolutely deserve. So thank you. Let me bring everybody in before we do anything more. Bring everybody in, guys. Put your hands together. Dr. David Perez. David, thank you again. And I would love to have, you mentioned his name was Tim, who was doing work, I think in Kansas City, you said. I would love to have him on as well, if he would like to share.
Mike Waters.
Mike, oh, okay. Oh, yeah. Okay, I know Mike. Yeah. Okay. Yeah, I can reach out to him. Yeah, and again, I'm overjoyed to have you present today and Reid as well, and all the guys. Jarod, go for it, sir.
I have lots of questions. Okay, so first question. So when you had the 4 section 1 and you were showing on your incredible modeling software you built, it looks so good, man. So it looked like you were able to take the fields of each of those and like focus them and overlap them there in the middle.
Yes.
I was wondering if that's a linear increase or if it's a curved exponential increase when you're able to focus multiple ones together like that.
It's actually exponential.
That's what I was hoping. So
we actually have an interrogator that you can move your cursor to the field, interrogate it. It will put up the sample that you interrogated, and we can make a complete list of the points of where you're at on the overlaps. So, I mean, I didn't want to show that part because we're getting into the secret sauce stuff of it. But the software allows you to actually make to see the exponential curve. As you probe all those points, it will make a graph for you and show you the characteristics of the curve.
That's so cool. The follow-up question to that was, so the V in your VEM, right? That has a specific angle that you've been using because there's a sweet spot there. But since you're now overlapping and you're having to point all those, in a certain spot, are you trying to get adjustable aperture there?
We have always, we've gone from 50 degrees to 75 degrees. And depending upon the engine and the size of it, like I said, we've built 24 engines of different characteristics and have moved forward with them. So to answer your question, the Mercavec geometry specifies 70.5. It came up with that number, but that's what we use as a result of thousands of experiments of opening and closing these things. I should have got AI about 15 years ago because it would have helped me advance this damn motor 15 years in the future. Because it's been empirical, and I can't tell you, to set up an experiment, the recorders, all the cameras, it takes like an hour and a half to 2 hours to do one experimental run. And then 8 hours later, you wonder what happened to the time, and then you got to go teach, and then you got to do this, you got to do that, take care of the kids, and whatever. I mean, that's just the way it is, the life. It's very intense, say the least.
So the last question that I got, and I ask this every time you come and present because I really want to see this someday. A 3D fractana. So So you're starting to get there now that you're arraying them and getting there. But a completely 3D one, have you asked your AI yet about building one of those?
Say that again. A 3D what?
A 3D frag antenna. So you've been doing 2D antennas, right? But you could have a 3D version where it's focusing all those fields together into one spot there, right? Wherever you want. So I was just wondering if you've looked into the 3D version yet.
Well, believe it or not, you asked that question, that I have a design for a 3-dimensional fractal.
Yes.
I did it without AI. Okay. I did it on paper and pencil. I designed one that it's a cascading fractal. And that would mean that it would have 18 iterations. And AI detected the iterations of this current that it builds up into fractals. Because we didn't understand until this thing started to do the analysis. I actually fed into AI the board. It analyzed the fractals. I gave it an individual fractal. I gave it the entire complex of a board and an engine, and it analyzed all of that stuff. And it married it up to our relativistic equation. And that was the most intriguing part of this whole thing, is I had this equation sitting around for, I don't know, 10, 15 years. And I fed the thing in and it said, hey, this is a space metric equation. It's a modified Lorentz transformation, but it's taking in consideration frequency and on the velocity, longitudinal waveform. And guess what? The Markovic geometry, the fractals, the amount of iterations that you have in there, that's what makes it go. I mean, simply put. So you're right. A 3D Koch curve with 18 iterations on it. I don't know what we'll do. I mean, you may not even need quad engines, but that was the only way I could figure out. Instead of building an engine that had 10 or 20 pound pulls to get to space, my idea was that I noticed on these experiments that moved the torsion bar long ago, that each engine has a different fetch point. In other words, a focus. And the thought crossed my mind, why not take an engine and cross the focus points and see what it does? You know, it's almost like Ghostbusters. Remember when they took the three stupid arrays? For some reason, that image crossed my mind, and I said, why not cross the engines and make a harness, a gimbal, and adjust them? And that's what we're doing. And it works.
That's amazing. You know, David, if I could interject for a second, you mentioned, you know, like AI 15 years ago. I've had kind of the same experience with my own work. It took me, I would say I'm probably about a year behind the curve in terms of AI. And I tell you, I've been wishing and wishing that I had started using it like at least 6 months before I did. You know, but part of that is, I think all of us are still early adopters, right? We're just kind of coming into it when we have time to get around to it. So,
it's amazing stuff. I had one of my engineers. They're volunteers. We don't pay them. They're mechanical engineers from UNL, and they came in and one of them had was beginning to look at the signal analysis, and he used AI. And he brought it here. I'd never used AI before. You know, everything was empirical, right? You know, the old school way, paper, pencil, duke it out, you know. Anyway, he brought his stuff in on his computer. I was just dumbfounded. It wrote all this software, and it had all these magnificent displays of actual energized or PowerPoints and the influence of the fields from the one point to the other and different frequencies. And I said, I'm going to get that. And so that's exactly what I did. Was I bought the $100 a month version, and in 4 weeks I built 9 software packages.
That's amazing. Absolutely amazing. Joel, you had a question, I think?
Yeah, a couple. So maybe to complete the question line of Jarod, the 70.53 degree angle that you found, you probably did a force angle sweep, right? And so my question would be, is the force like going up like this, or is it like a curve that tops around that angle?
Believe it or not, when you go on either side of the 70.5, it goes down.
Yeah, that's what I believe. And that's very interesting because it correlates with the theoretical thinking that we've been having in the background. So that's very interesting that you're finding that. And so also for the development of the software, you are developing it for yourself, or is it something that you want to also give to the public? For example, I'm not sure if you're aware, but there is a project, it's called Warp Factory. It is done by university people, and it's a very good GitHub project on which you can model like IQPR drive type of stuff. So if you haven't heard about it, you should tell your Claude about it, because it probably can learn something from that software package, because it is professionally designed to model.
There's a couple of software packages that I made that estimates time to go to planets. It allows you to set up engine parameters, how many newtons, if it's a quad, is it 10 units together, and it calculates the actual amount of pounds of pull and all that. And then the time it takes to get to Pluto, for example, and it gives you the percentage of speed of light and all that. So we're releasing that one. We did a podcast with Jerry Wills, and I sent that software to him, and he's going to display it and give it away. And on our website, on our Facebook, we're offering it as an open piece of software. Plus, we have a little, it's kind of comical. It's a simulator, but it has the Earth and whatever planet you're going to go to, and the bluebird flies to it. But along the way, it has a tag, an information tag that shows speed of light, how percentage of speed of light, how fast you're going, what mass, and all this other kind of characteristics that you would want to know if you're going from point A to B, and how fast and when you're going to get there. For example, our Model 15, which we've always, Model 19, which we've always talked about with 15 newtons of force, could get to Mars in less than 3 days. With our current, just single engine, we threw it up there with a support package. And, but the whole concept of space, if you can't get there quick, you're subjecting yourself to all the radiation and all the nasty stuff in outer space. And my concern has always been get the astronauts there quick, get them there safe, and you don't need the fuel. You don't, and think of the logistics. It's going to take 10 months to get to Mars. Look at all the garbage you got to bring with you, you know, groceries and everything else. Well, if you could get there in 3 days, you could cut down on the groceries and put those provisions to stay on Mars for 10 months if you wanted to. I don't know.
So maybe my last question would be, the power of latency is very fascinating. Do you have some do you have some ideas or some correlations, maybe thermal cooling or capacitor discharge, or do you have any ideas what that is related to?
Well, it's actually is the rear field is dissipating. The The forward pull of the motor is dissipating. And so it's all working in concert, despite the fact that the power is off. Remember, you've got a lot of nested current loops with the fractals and the iterations. And until that burns off or dissipates, you're still moving forward. So I used to have ideas that it was kind of like big magnetron tubes that when you turn them off, they still work because there's a kind of a latency. There's electronic puddling that goes on to the plates. And I kind of associated it to that, but that's not really what's happening here. What's really happening is that the current flow is dissipating, and even though the power has been cut off, it's kind of like it's storing up like a battery. It's dissipating its charge and going back to ground level or neutral.
Thank you.
I kind of wanted to add on to that real quick, if you don't mind, Sir Dave. So I was actually, during one of my experiments, I think was the first time that we actually really saw that.
The latency.
Basically, yeah, the latency, which was really cool. One of the things that is really interesting is there is a single inductor loop in the system. However, that shouldn't cause the same amount of time delay that we saw for the drift to still happen after power is cut off. Because we have it for a point where we can actually see that, you know, on the needle, power cuts off, it still keeps moving for 15 seconds. So that's enough time that capacitors wouldn't do it for that long and inductors wouldn't do it for that long. So, you know, could it be a warp field dissipating? That's kind of, you know, time to now experiment and test.
I believe exactly that. It's a warp field dissipating. Going back to like any ion drive, once you ionize it, throw it out the thruster, out the nozzle, it automatically returns to the original state of the Xeon gas. So a neutral, you know, it goes back to standard atomic structure. So, you know, realize that the bubble or the path is literally fabric of space is going over this thing. That's what's pushing us forward, is fabric of space in that respect. So there's a whole new science. It's a whole new entity of exploration. We don't have all the answers. We're coming close, though. It really is exciting stuff. I can tell you in the last 4 weeks, the door has just blown open with ideas, information, things that I didn't know before. I suspected, but now it's confirmation.
I have a question for you. Okay, so you're warping space. Have you looked at the vacuum energy of it? Because what happens is if, let's say, example, if space is energy and stuff like that, vacuum energy, it depends on its value, you know, if you want to warp it. Okay, if it's huge vacuum energy, like 10 to the 120th that QED you know, proposes, then you need that much energy to warp it, or and stuff like that. Or is any in my, I mean, I cut it short. Do you even consider vacuum energy or not in your equations?
Vacuum energy?
Yes.
No.
Okay.
No,
you.
not at all.
Yeah. Now, guys, if I could jump in really quick. So Mohammed is actually not able to join us today. I'm going to have to reschedule him. He might be able to come later, but so we have kind of an open block. If you guys want to continue discussing this, that is totally cool. And other than that, we could go to, you know, like lab updates and stuff. So it's up to you guys. Jarod?
Questions for Mr. Perez?
Yeah, go for it. Go for it.
So I was wondering, it wasn't quite clear. Have you actually built a 4-section model yet? Or have you built at least a multi-section? I thought that you'd done like 2 stacked above and below each other before, but have you done, like, physically done the interacting separate thrusters?
Are you talking to me? Oh, okay. I'm sorry. There's a guy mowing the lawn out here, and I don't know if you can hear it, but I can hear it, and it's interfering with me hearing you. Go ahead. Ask a question again.
The multiple thrusters that interact and create the interaction field.
Yes.
You had your simulation where you had 4 of them. I was just wondering, have you done any physical tests to make certain that, you know, you're getting that exponential curve for the multiple ones interacting like that? I think you've said you've done stacked before, but I really like this side-by-side pointing together thing, and wondering if you've done that.
Yeah. I actually, about a year ago, our lab is modified garage like most of everybody else here has done in the past, unless you're fortunate to have a big full space, couple 100,000 square feet of testing area. We don't. We have a 3x5 Faraday cage, and the quad system that I put in there, I burnt up an engine because it got too close to the edge of the Faraday cage. So we're limited in space. That's why I was going to the 1 foot models, and we have several of those, and I have the parts that just came in that we're going to be building to actually do that with the 1 foot models. It won't be as dramatic, but I'm really holding out for the M19 engines. I've got enough of those that we carved out, we lasered, fiber lasered, to build 4 of those engines and do that one. I almost want to, well, try to go out and find a space that I can run this thing. We're not there yet. We've got funding in the wind and all this kind of crap. Every day it's another thing, but anyway, we'll get there. I don't know if that answered your question. We've attempted to do it, and we're sorry that we did it because it was too tight in the Faraday cage, and we ended up arcing an engine. That's not good. And we also arced one of our linear amps. So, see, those things are extremely precious to us. They're $10,000 a copy, okay? And in the past 10 years, we've blown up 4 of them. So we've had to rebuild, and that's 40 grand out the door. You know what I mean? It's like on an adjunct salary, you don't make a lot of money.
Another reason why I did the low power test, so I wouldn't blow one of those.
That's right. And that was another reason why. Yes. You know. Hey, what do you guys feel about with the disclosure that all of this is going to be nil? All the work that we're doing on all this stuff is going to be revealed that, yeah, the government already has it.
They've been saying soon for 80 years.
Yeah, I think I'll get to Mars before NASA does. David, I'm looking at this picture of this thing, and you got a whole bunch of, I guess, hexagonal holes in this thing. Was that just to lighten it up?
Oh, that was to save on the plastic. Yeah, it wasn't to lighten it up, and it wasn't to keep it cool or anything.
So all that blue stuff is plastic?
Yeah.
Oh, okay.
It's 3D printed.
Oh, okay. And
we use,
I don't know, the snowflake looking things. I guess the fractal antenna copper snowflake looking things. Can't they just be I don't know, vacuum deposition? Or do they have to actually be cut out of thick metal and mounted on whatever isolators, I guess, or something?
Well, what we found was
blue plastic.
the thicker the material, the better the concentration of the current that it captures on the iteration.
Huh. Okay, that's something in the RF world. That an RF radio antenna thing. I don't know anything about RF.
Well, if it was a straight wire, it'd radiate out in all directions. And what you've done here is taken like a 12-foot equivalent antenna and put it into 17 inches. Like if you took a string of 17 inches, that's basically what the fractal antenna is composed of. It has actually has the same gain as a 12-foot antenna, except it has additional properties of this current loops onto the fractals themselves that convert into longitudinal waveforms. And that's really the key, the whole thing of building this thing. But the other aspects of it, it's the building of the field. You can't, like I mentioned, you can't just snap a button and the field come up. You have to build a field, a warp field. It's not an easy. There's a lot of process that goes into doing that. I've been doing it manually, and I would say probably 40% of the time I was successful, 60% no. But as we've gotten into more of the how and why of how to build the field, it actually worked all the time. We just didn't have enough time to build the field. That's what it came down to. So we've improved our startup. It's an evolution, you know. You don't go down to Kmart and get a warp drive engine, you know, and plug it into your computer and say, okay, beam me up, you know, energize me, let's go. It's not, I don't want to say it's difficult. If it was, I guess I wouldn't be doing it, but it's very labor intensive. I can tell you that. To do any of this stuff, well, like you analyze all this materials from these crash sites, it's very labor intensive, you know, and it's a passion, and I got a passion for this. I intend to lift that craft off of Council Bluffs Airport and be the first warp drive aircraft or spacecraft ever to lift off the ground.
So
because if it works in terrestrial space, it works in outer space. And by the way, it had been tested in a vacuum. So I know that's one of the other questions that everybody has in the back of their mind. Well, it works in terrestrial space. What about a vacuum? Well, the Germans tried to copy our design. They got results, not what they wanted, but it was tested in a vacuum and it worked. So
by what German group was that done? Do you remember?
I've seen their paper. I don't remember the name off the top of my head.
Tim can
Okay, we will find out. But thank you. Yeah, but I just wanted to state, I think it's very interesting that you're not only seeing a force, but you also have this redshift. You have the latency and the very strong angle dependence, and you have that all together, right? That's very, very fascinating. So as the peak is sharp for the angle force sweep, that to me looks that it's a geometry selection mechanism and not just an ordinary field coupling, which I find very interesting, especially. And so what I wondered is the redshift and the force, they should correlate in time, right? So because it's basically the same, right? The redshift is showing you how space-time is warped, and the warping of space-time gives you the force result, right? So does that also hold true during like the power of latency? So if you do the experiment and you have you're measuring the redshift with a laser or something, is the force decreasing in the same way as the redshift is during the power of latency time? That would be a very strong positive signal.
I haven't analyzed that yet. that's something that just recently noted in past experiments. We used a Mylar mirror with a laser on. We would put engines up on not on a Newton scale, but we would use springs, and we'd hang it down on the spring, and then we would calibrate it with 100-gram weight, and then find out where it goes with 100 grams. And we had a real simple graphing paper and a pencil. And when the laser reflected off of that mirror on the engine, it would move in a downward direction, pulling. And then we would physically mark it and measure, what the results were, and attribute how many grams of pull did the engine have at that set amount of power. It was very primitive in the early days. We've gotten much more sophisticated since then. But during that time when we used the lasers to measure that, we got some really kind of interesting results. I set up 3 independent pen lasers and shot it through the field, and we actually poured smoke into it, got some smoke and poured it into the fields, and literally saw the fields bend, the lasers around the warp field like that, bend it. It was somewhat, it was kind of interesting on that. So we knew there was something there, and now with the software, we can, basically prototype it and advance our designs. And that's all.
You quantified that amount of bend?
What's that?
You quantified the amount of bend? Like you saw it, and did you figure out how much it bent?
At the time, I didn't measure it. I was just curious to see what would happen. Alcubierre talks about this tidal action at the edge of a warp bubble. He said it's very violent. And so we account that we're using very low level power to engage a field, that maybe there isn't that kind of violence in the low power end. Whereas he was talking about a 1,000-meter warp bubble with this violent tendency. But the empirical account of Bruce Gernon, when he flew his aircraft from Bimini Island to Miami Beach, pilot report. I mean, he went like in a second from Bimini to Miami Beach in the warp tunnel when he encountered those 2 thunderstorms. He was surrounded, and he went through this thing with seeing blue sky on the other end. Other pilots have encountered the same thing. This is what led to all of this, what we're talking about today, of these pilot reports. And the thing about what Alcubierre had predicted, this pilot went in at 10,000 feet. He said warp bubbles will travel in straight lines. They're influenced by mass, because Gernon went in at 10,000 feet. He exited at 10,000 feet over Miami. The problem is, if indeed he was a straight line, he went into the warp tunnel, he would have went out into space 100 miles. He actually went with the curvature of the Earth. This presents another issue, that when you go into space with a warp drive, you have to account for the large masses that are around you. You have to deviate. In order to fly a straight line, you've got to navigate and pre-predict all your corrections to fly a straight line. we have a lot more work to do than meets the eye of just lifting up off the ground, you know.
I have a question for you, David. Now that you've got AI as a tool in your toolbox,
Yeah.
I know that the thickness and materials. Joel, could you please mute? Thanks. I know that the thickness and copper, aluminum, or whatever you're choosing to use for your material for the fractennas, like those all play a role.
Yes.
I was wondering if you've started using AI to optimize for both the physical dimensions of the thing. I saw you had like iteration count, but like actual thickness for skin depths and for like overall power levels it can take. Because I know you got a lot of current run through that thing, right? So the physical characteristics of the thing, optimize that, and the material characteristics, because I'm certain that, you know, with the frequencies that you're dealing with and skin depths and resistances and impedances, all that stuff, that different materials probably are going to be better than other materials. So matching those two things to like up the game, maybe up to 10x or more, you know?
Yes. Actually, I asked Claude about fractals and what potential improvements could be made. And it wasn't due to thickness. It was due to the material, silver. One of the ideas that I've had is platinum, not making them out of platinum, but doing copper fractals first, nickel plating, silver, and then platinum on top of it. That's the most conductive material that you can get. But it kind of harped on silver. It didn't like aluminum because of the atomic nature of it. The copper has more, you know, electrons to jazz around into the metal. So thickness makes a big deal, but that three-dimensional, the cascading of the iterations will make a big difference, which it only said more iterations you got, the better current flow that you'll have, the current puddling. So that's what I'm after.
And I could be wrong, but in my quasi-crystal research, I thought there was a Coach Curve quasi-crystal out there, which those are super cool because now you're stacking the energy beyond just the 3 dimensions, right? So quasi-crystals have this higher dimensional nature to them, which is potentially very useful if you're talking about metric engineering, right? You want to stack as much energy in a small spot as possible. Well, hyperbolic space is a great spot to do that, right? So yet another thing to consider asking the AI, not just 3D, but 5D.
You know, there are so many different ideas out there that I always have to remain very focused because I'm interested in so many things. I could be diverted and take years to solve one problem and not solve the other problem. So right now, our focus is quad design and overlapping of the fields and lifting up Bluebird off the ground as a demonstrator. That's really that's the main focus, and that's where all the funding goes to, is to get that done and go to space. That's what I want to do. I want to have coffee on the moon. Mars, lunch, maybe. I don't know. But I want to go faster than the speed of light. And I'm telling you, it's definitely possible. It's just a question of energy and the design of the engines. Maybe it will take 100 engines, you know, in a big circle to do it. I don't know. That's unknown right now. But
yeah,
that's
to
my
go
goal.
faster than the speed of light, you need to basically isolate yourself inside of the warp field, because that way you have real space inside with the spaceship, and then the distorted space around you that's pushing you through space-time. The space-time can move faster than the speed of light, but no actual physical matter can move faster than the speed of light.
I asked Claude that, and it talked about superluminary speeds, because we know that it's possible out there. And it had given some ideas of superconducting, using superconducting material to do the same type thing of what we're doing with our fractals. I don't have the facilities to do superconducting stuff. I don't have iridium wafers. I don't have any of that kind of. So we'll stick with what we got right now and make do and make history with what we have. I can say that. We'll get there. We'll get there. I'm confident.
On the note of whether or not it's doing the superluminal thing and going back to the laser thing, it's worth noting that Mark Sokol and I, we were working on this rubidium clock thing. To be fair, Mark did most of the work. But the gist is you can take old rubidium clocks that used to be on a cell tower, right? And you can get them for super, super cheap. And you can take those things, sync them up on your scope, on your oscilloscope, and make sure that, you know, they're all the same phase and everything. You're getting very little drift. As long as there's no magnetic fields nearby to mess them up, you can use those to detect any changes in space-time, any changes in the rate of time, right?
Really?
So, yeah. Now, again, you false positives galore. I was showing Mark when I was there. I was like, look, you bring a little magnet in close to this thing and you watch the phases go whoop. So, because they operate by having a little, kind of like those old mercury thermometer things. It's got a little piece of liquid gallium or liquid metal inside there that it's using for the rubidium reference. Liquid rubidium. So that's, you know, that can be affected by magnetic fields there. So you got to be careful about that. And I know you got magnetic fields galore going around this thing, but it could be possible, like if you were to shield the magnetic field somehow and have these clocks all around outside the chamber, you could end up potentially detecting if time is flowing at a different rate near this thing, which, I mean, that's getting, it's almost smoking gun territory.
You know, we did mechanical watches. We placed one in by the engine and a control watch, and then one outside and then one inside the field. And we didn't, well, we did it for like about a half an hour, but we didn't note any difference in the time. I think in the compression itself, there's time dilation internally into the bubble. It's the same time as the ground time. There isn't any difference.
So the change in the rate of time is a super small amount. And I bet with the soft modeling software you have, you'd already be able to estimate this. But for a reference point, if you're standing at like sea level, right? The rate of change difference between the top of your head and your feet is about 1 picosecond per meter, or picosecond per second per meter. So basically the top of your head is experiencing time 2 picoseconds different than your feet, right? Oh. And that's why the satellites, the geosynchronous, you know, GPS satellites, why those things have to have so much of an offset is because the rate of time is going different for them by like a couple 100 picoseconds at least, or like a few thousand picoseconds. Like it's a lot relative to us standing here, but that's why a mechanical watch, like if time is traveling at that kind of rate, you're talking like spaghettification type stretching, like that's crazy amounts compared to like Earth gravity stretching amounts.
Yeah. I used to work with satellites. We had that problem long ago. Had to reinitialize the clocks all the time to know where the nadir was. And that affects not just geostationary, it affects polar orbiting satellites. Yeah, it's a real issue.
So if you can show with yours that it, instead of picoseconds, you're like 6 orders of magnitude, you know, better, you're like nanoseconds changes or something. Like that's a crap ton of warping right there.
We haven't gotten there yet, but that's a good idea. That's a good idea. How much do those things cost?
I think each one was around like $300 used. So for $1,000, you get 3 of them, right? You can even find batches of them. Sometimes you can find a batch of like 8 of them for like $1,000 or something if you get lucky. They come in 10 megahertz and 15 megahertz. And the reason why they're getting rid of them used is because they have too much drift already. So you are losing out on that. But when you take 2 of them and you let them sit and you let them line up, the phase difference between those means that instead of being in the megahertz range, right, which is hundreds of, sub microseconds, when you get 2 of those and you line them up, the phase difference between those, you can get it down into the very, very sub nanosecond range,
Wow.
which is pretty cool. But again, they're super duper sensitive.
That'd be interesting.
Last time.
That would be an interesting experiment. We keep moving on here and we get a little more funding. That would be interesting. There's so many questions to be answered. It's been I have nearly spent a lifetime doing this stuff.
The other one would be a laser with Faraday rotation. So depending on the strength of the magnetic fields in your sweet spot, focus spot there, those are pretty straightforward tests. And I would say that those are going to be even cheaper. And you can do pretty straightforward calculations to determine the amount of Faraday rotation that you're experiencing there and the amount of magnetic twist that is happening in that area. And if you're getting a decent enough amount of that, then you can immediately prove to a ton of different people that matter, like, this is an important thing just because it's doing an insane level of magnetic rotation of a laser.
Sure. Yeah, very interesting.
Yeah.
We have some of those tools. We'll be able to do something.
Well, and guys, we're at the bottom of the hour. We can keep talking about this if you want. Or we could go to lab updates. I'm just letting you know. So it's whatever works for you guys. Okay. Then all of a sudden it went quiet. Well, why don't we do this then? Why don't we go, if it's okay, let's go to lab updates and we'll do that. But before that, guys, let's put our hands together one more time for David Perez. David, thank you so much. This has been amazing opportunity to see like the progress that you've made. I'm so excited.
Well, next time we'll be able to show you a whole lot more. I just didn't understand more about the screen sharing and what I had to do because we got a plethora of all kinds of neat stuff.
Okay.
We'll show you an engine startup next time.
Yeah, no, that'd be awesome. I'd love to see that.
Okay.
Well, let me do this. Let me ask Drew, do you have any updates for us? Do you have any lab updates?
I didn't put anything together, but we're getting ready to move into our new facility. That's going to be a nightmare because we got to tear everything down in the hangar and move it all over. I think we're fully funded now, so we're not going to be eating beans and rice forever. Hopefully, we'll be able to afford a hot dog with our beans and rice. Let's see. You got the open air demonstrator making thrust down to 230 volts, which I don't understand, but apparently it does. And pretty much we're just working on the open air stuff is still pretty hit or miss. You can build 10 units that are exactly alike, as far as I can tell, and maybe 3 of them will work correctly and 7 of them won't. I don't understand the not work correctly part. They look exactly the same. They run on the same equipment, but we have some. There's something about open air. There's something about that polarizing the air molecules or something, and we gotta jump through some really weird hoops to make this open air nonsense work. But everybody wants to see the demos, sitting on a desktop. They want to see the scales move on a desktop, and they don't want to look in a vacuum chamber window to see the scale change. So stuff that's flawless in a vacuum chamber is a nightmare to operate in open atmosphere. It's not a matter of whatever it is, ion wind or anything. We've beaten those problems years ago, and our design eliminates the possibility of ion wind. So it's just working in air. It's a terrible thing, and we've got a couple more podcasts to do, and they wanted to see some demos. And we've got Dr. Charles's super awesome presentation to the Friendly Electrostatic Society of America coming up in June, and that's an open air demo. He wants to do it on the table in the middle of the buffet. So that's where we are. We're moving and trying to figure out why it's so curiously difficult to get stuff to run in air. That's it for sunny Florida.
Drew, thank you, man. Thank you. And then Jared, do you have any updates? Because I know you're putting together a lab too.
I am, but the big thing that I'm doing is you asked me to put together that Llanilar presentation while I'm in the midst of scrambling hard to get ready for the McMinnville UFO Festival, where we're going to have you and David Chester and Matt Sadagis, and we're going to go visit Isaiah's lab. And I think we got some other folks coming visiting too. So it's going to be a fun time next weekend here in Oregon. So I'm trying to get this place all spiffed up, make sure that your bed is nice and ready and made for you so you have a comfy, clean place to sleep.
Well, thank you. Yeah, I'm taking the train and a bus. So, because I'm too lazy to drive. Although, to be honest, at some point, the train and the bus, the pain in the butt adds up there. So, yeah, no, that'll be exciting. I'm really excited. I'm excited to try and get some photos and video of your lab and what you're doing, as well as what Isaiah is doing, because I know he is pushing really hard on the Searle effect stuff.
Mm-hmm.
So yeah, guys, if you want, should we just do like open discussion? We could go back to talk about David's work or whatever. I mean, so Denny is coming on at 5, and that's about 2.5 hours away.
I have another question for David.
Sure. So do I.
Yeah, go for it. Go for it.
So David, the coax that you got going into a single VEM, you're running 1,500 watts through that thing. I'm curious, do you know how much of that is current? How magnetically polarized is that signal?
How much is current? Well, the only...
Because you can be 50-50 polarized. It can be half electric, half magnetic. You can be 90-10. It can be electrically polarized, very linearly polarized, right? Or very magnetically polarized.
Well, the RF that comes out, which we measure on our meters, is all in watts of power. We don't have current meters on there. So it's just raw RF that comes out of the linears. We go 0 to 3 watts in, and you get, with our combiners, we get up to 3,000 out. And we throttle up to that. But we typically run 1,500 watts as a standard test, only because the linears can get hot. And that's a drawback, but we're going to remedy that by putting Peletier diodes on the copper spreader on the top. We don't have air conditioning, but the equipment has air conditioning when you need it. I mean, we test in 8 degrees, 4 degrees. We don't have any heat or air in the garage. So we've actually tested 130 degrees in the garage, and there's no variation. That was another interesting thing. And I'm glad we kind of did the poor boy lab because it told us that no matter how cold it was or how hot it was, the drive did the same thing. same power, the same results. So that was encouraging. It had nothing to do with any kind of terrestrial heating and cooling.
And those RF cables, what power level are they rated up to for the coax going into the VEM?
We do test with different levels of coaxial cables. We have some that will allow us 2,500 watts. We have some that will allow us 2,000. The preferred cable that I'm trying to attain is 6,000 watt. It's a high, lightweight aerospace cable, except the manufacturer wants me to buy 1,000 feet of this stuff at like, $35 a foot. And last time I checked my paychecks, they don't even come close. So yeah, it's kind of, we're limited. If we had the right kind of cables, we could fire up to the full limit of the system, but we can't right now. So we do have some lightweight aerospace cables that we use, and they're rated for 2,000. And that's why we kind of keep it to 1,500. But my license only allows me to go to 1,500 anyway. But in a Faraday cage with a deep earth ground rod, which I have, I can juice it if I want. But I just kind of keep it under the norm. We like to be silent to everybody else in the world. I mean, we're out there in public, but I mean, as far as electrically, we're very quiet. You don't know us. You can't hear us.
And it's CW or it's pulsed, because I could see one being a lot more like if you have an RF leak in your cage, right? The FCC is going to come a knocking with one of those a lot more than the other one.
Yeah, it's CW actually.
Yeah, that they don't like it when you just wash out the whole spectrum.
Yeah.
What's CW?
Continuous wave.
Like always on, no pulse, 100% duty cycle.
Yeah. Yeah, and besides that, I tried pulsing this thing a long time ago. You can't pulse this. It doesn't work. Because you have to build a field. And the field has to be maintained. Once you maintain the field, you can bring it up to 6,000 watts if you wanted. But the thing is, the initiating field has to be built and it has to be maintained. You can up and lower the throttle, and it will, but once you've passed the initial threshold of building the field, you have to maintain it. And if you pulse it, you lose it.
I would hazard a guess that based on what you said about the decay time of the field, that all that energy that goes into building this thing up, once it is built up and once you've stirred the ether or whatever it is that it is doing, once you've gotten to that point, you might be able to get away with less than 100% duty cycle. You might be able to get some kind of pulse in there where you can maintain the field for less than full power, which if that's the case, I mean, your power to thrust level just went way better.
Yeah, I have a pulse generator that I injected into that, and there are different schemes of doing it, sine, square, but the initial pulse, I may have just pulsed it too slowly. It should be faster pulse.
Yeah, because 1 watt per second is the same as 1 billion watts per microsecond? Yeah, per microsecond, right? a million watts per microsecond is 1 watt per second. So if you get your pulse rate down to a fast enough amount, you can dump a lot of energy for not a lot of cost, right? And if you're dumping it, often enough within your 1 second window there, you can be dumping lots and lots of power compared to the amount of power that it actually took to do it, right?
Yeah, one of the things we're looking at was trying to pick up kind of like an antenna structure. I'm not quite sure how we would do this, but to pick up the drag of the latency and recharge. What could hold that kind of energy? A Leighton jar. We're back to Tesla now. Lightning in a jar, so to speak. Those kind of thoughts have crossed my mind. But again, to be defocused is the issue. You got to be focused and keep pushing forward. The other stuff will come in time once funding comes and all that other razzmatazz, hiring people. But right now it's just 6 volunteers and me doing this all the time, and that's how it is.
So what's the field? I mean, is it an RF? The warp field thing that you're making, is it an RF field? Is it just a ball of RF energy interacting with itself? No. It actually is. It's a structured reactive field. It's not RF. The actual output of this thing, it's a force, a longitudinal force, the wave form. So if it was RF, it would just radiate out. There's no pressure to it. Okay. RF just propagates a straight line wire. In this case, but the fractals are key with not just puddling the current in the fractals themselves, but it's the waveform that it forms that forms the compression of the fabric of space. Longitudinal waves actually have a lot of power. I don't know if you're familiar, there are a lot of lighting systems now that are longitudinally based. They save over 30% of energy. Transverse light forms are very inefficient. Longitudinal waveform light sources are extremely efficient. You can save up to 30% of your electric bill by going to longitudinal. Now, I just mentioned that is because longitudinal has a pressure, and it's this pressure that forms this bubble that the fabric of space just flows over and pushes you. And that's what we've discovered. And, okay, so the antenna, I mean, those little copper things that look like snowflakes, they're antennas, right?
Well, that's
They're
what
not
they
antennas?
look. That's what they look like, but the end result of them is that they're actually emanating out a longitudinal field.
Okay, so you're putting RF energy into a thing that starts out as an antenna,
and it converts it.
Okay, so they don't radiate. There's no RF energy coming out of that copper. It's all getting converted into messing with space.
Well, there obviously would be inefficiencies there. A perfect radiator, a perfect fractal would then take all the energy and push it in. Our fractals are not 100% perfect. They are, about a 1.1% off.
So they don't radiate, they just mess with space.
Essentially, yeah.
So you're
So-
dumping energy into a piece of metal, and
Yep.
it's dumping that energy.
It changes the it changes the
The
fabric of
universe?
space. It
Okay, it
changes
doesn't
the
heat
fabric.
up. It doesn't radiate. You're
Yeah,
just dumping energy into it.
There's no noise. There's no noise. It has it cools the ambient air around it by 4 degrees, which we found, and the signal that we use, the RF frequency that we use, is representative of a thunderstorm at the freezing level. But the output of the engine is that you would get, if you had a spectrum analyzer there, it would give you a frequency emanating out of the engine, but it's the harmonics of it that influences the fabric of space in this case by creating a bubble around, well, a path around the actual engine itself.
So for these longitudinal modes, like if you have the slinky string, right, and you're doing it, you know,
Yeah.
at a harmonic,
Yeah.
right? That node there
Yeah.
on the middle of the slinky, that's a longitudinal mode. So what you're doing is you're creating longitudinal modes with a single fractana. You're stacking those up against each other to create a structure of these nodes, and then you put multiple ones of these together. And now you create a structure of these structures together. And it's like the energy density at that node is getting greater and greater and greater as it gets focused more and more.
And we're actually shaping a field. If you noticed in those diagrams that I had there, see that this is what is, it doesn't radiate, it shapes the field. If you notice the nodes on the tripole fields going into the engines, and there's a null area, that's where we put our cables. We actually inject our cables in the middle of the engines because that's a null area. It's unaffected. We're controlling space. This is what's so phenomenal about the motor. It's revolutionary. We're actually molding the fabric of space with the fractals. And in between the sets of the tripole fields is a null area. And you run your RF cables into there, and they're unaffected at all.
So I don't know anything about RF, guys, but whatever's making this RF energy is a box that you plug into the wall somewhere, right? It's an RF generator, right?
No.
Radio frequency generator. It's
It's
like a radio,
there's an exciter that then goes into the linear amplifier, which is the frequency that we have engineered our fractals to.
Okay, so it's a radio of some kind. It generates an RF wave that runs down that wire in some way, shape, or form.
Yeah, basically, yes.
Okay.
But when it gets to the engine, it converts it into longitudinal waveforms.
Okay. Before it does that, what if you shrunk down the radio engine, the radio frequency generator, and mounted it on each one of them little fractals? What if you had a little tiny one that you could mount on those fractals? Would it work? I mean, if you got rid of the wires and the thing that's sitting over on the side and the 5 tons of radio RF generator, and you put it all just in a little tiny sugar cube, and you mounted it on the whatever that snowflake shape thing is.
Yeah. One of our future designs is to actually take a linear amp and put it on the back of each tripole field. So there are, or all of the 4 tripoles are independently controlled. We're not there yet. that estimates like $200,000 to design the module to stick on the back of the engine.
But the phase correction you could get with that, oh man, you
Well,
would get.
you know, right now we're fighting 50 ohm wiring and pi tuners and all that. It would eliminate all the tuners because everything would be direct drive to the fractals. You know, we're fully aware of it. I mean, it's not like we never thought of it. We have. It's just that it's really money. It's funding. That's what's really driving. So we got to use what we have to demonstrate and to provide more of a, you know, if we can lift that thing off the ground, like we've been talking about with the quad lifters and all that stuff, then that's the direction that we'll go when we can get additional, well, we can get the full funding that we need to do the innovation of taking the linears and putting them directly onto the tripole fields and independently controlling them. That will be phenomenal results right there. Yeah. So, I mean, we're fully aware of in my designs that I have, which are all over the place. It's all money dependent. And develop of a new linear, 200 grand easily. That's miniaturized. The ones that we have are 10,000 a piece, and we can replicate. We can repair those. But yeah, the new linear that we want is big time money. I mean, to other people that have the funding, it's not an issue. To us, on an adjunct salary, you know, it's an issue. So we're not getting there yet.
So can you tell me one thing? Because I'm with Drew, I'm flabbergasted. You're using electromagnetic waves, and what's the longitudinal wave? Was it made of electric field or magnetic field? I'm confused.
It's made of a electric field, RF energy.
Okay, so you're modifying the vacuum in that case, basically states, and that shapes the space-time, because that's what it is in that case. Because I cannot, you know, it's difficult for me to understand what you're doing. You're using electric fields and modify space, so creating gravity wells with electric and magnetic fields. That's what you're doing. Am I right? Or
Yeah.
I'm lost somewhere?
Yeah. Yes, you're right.
So somehow the little piece of metal is oscillating whatever it's doing, and it's affecting the space around it. It's modifying the space-time continuum around it.
Yeah, that's exactly what it's doing.
But if you want to do that, you have to understand the vacuum energy, because if I don't know what it is, because the hypothesis would be the vacuum energy is space, and create basically, if the vacuum energy, you can squeeze it, and somehow you create gravity wells or stuff like that. I don't know what it is, but it has to, if you're using magnetic or electric fields, it has to be interacting with vacuum energy in order to produce gravity wells effects.
Well, unless that's an additional component that we've not seen yet.
No, but I mean, it has to, theoretically, it has to come from somewhere. I'm not a physicist.
But this is the point. Like, we're going now into the theoretical topic. So we have multiple experiments here at APEC that do work, even though we have no theoretical explanation of why they work and how exactly they do work, right? So I think this is also a point here, David, from your presentation, from your slides, and from a short internet search. I'm also like, I'm seeing you're describing your experiment phenomenologically. So you're describing what you're seeing, you're putting that in parameters, and that's very good, but you do not have a complete theoretical structure to explain what actually is happening, right? So you do not have the complete Einstein equation solved for that. So you do not have stress energy tensor gives this kind of space-time distortion and so on.
You don't have to have equations.
To have a complete theory, you need equations.
No, I know, but you don't have to be complete.
Yeah,
you can have
you don't need a
thought
theory to have
experiment.
something work.
You can have an idea, okay, without numbers,
Yeah.
okay?
If-
But you have to have that idea, at least.
If
Yeah, and he
Drew's
has the
stuff
idea.
and if Drew's stuff and David's stuff are doing the thing, and both of their stuff do not have anywhere close to the energy densities that GR predicts you need for curvature,
Yes.
right there, full stop. Like, don't even worry
Yes.
about getting off the rock. All of the armchair theorists out there who have nothing but time, of course,
They should
need
now
to-
listen up.
they need to listen up because something is broken
Yes.
in the model because their prediction is not matching experiment anymore.
Oh yeah,
Yes, and not only
even our
not only is it
crazy
broken,
energy.
we know the specific point how it breaks. We know that geometry is very important, that we have a specific angle. At this, you see the force. Next to it, you don't see it. So a very specific geometry gives rise to a new kind of coupling, which is not included in the standard model theoretical description of reality at the moment. And this is like what we've been saying in the background for months now. And so for me, as I work in Heim theory, that's actually very good, because in Heim theory, there is exactly this meson field type coupling between the EM field and the GR type interactions. And it should depend on geometry extremely. And it should also have like this steep shapes in the force angle curves and what you want to see. So this is all very exciting and very interesting, but we need to be clear that we do not have a complete theoretical understanding of it yet. But this is what we need to build towards.
The big
I got
the
another
big
question
number.
for David.
Drew, real quick, let me put this out there and then ask a question. The big number that the theorists need to pay attention to is the decay time, because in Drew's case and in David's case, when they try to turn off the thing, the fact that it's not an instant snap off, that there's a ramp down in both of those cases, suggests that whatever the background medium is that they are stimulating that is allowing them to push off of something or pull on something, that's the first place that they should start looking for superfluids or mesons or ethers or whatever the theory ends up
We
being.
know exactly why ours doesn't go off quickly. It's just down charge. We're literally injecting electrons into the dielectric. If we inject them into a dielectric that drains fast, things come down fast. If we put them into a dielectric and don't give them a chance to come out, it'll stay in there forever and it'll make thrust forever. So we know what the mechanism is. You know, it's injected charge. That's not a whole lot of and I got a sneaky feeling that's what's going on with David's stuff also. I think he's injecting charge into the substrate behind his antenna. That's why I wanted to ask one last antenna question. Again, I don't know nothing about RF, guys. I mean, I thought you ran the electron. I thought you ran the wave up the pole and down the pole and up the pole and down the pole, and that's what generated the RF wave that comes off the antenna. And that's what I thought happened, but apparently it's not. So Dave, you've got a little compact version, but you said it's just a tiny representation of something that could be real long. So people have been building antennas and running RF out of antennas forever, 100 years now. Nobody else has noticed this when they shoot a laser by an RF antenna. Does a regular RF antenna bend the space-time around it also?
No, you have to. The thing is that a laser will be affected when you have cross fields. There's a sweet spot that goes in between. And what we did initially was we set up some VHF antennas on a optical bench and regulated did experiments with distances, matching and putting the laser through and looking through a fringe pattern set through some optics. And bottom line was that we had when the system was off, the laser was full width round. And when the system was on, we compressed the laser beam. And that told us that what we were doing with the cross fields, in this case, the VHF energy, is that it did affect the laser. Now, if you just have an RF radiating element and you put a laser by it, it won't affect it at all. But when you cross fields, you will affect the laser itself.
Okay, so you're saying you're when you say cross fields, somebody doesn't know what that means. You're setting up a node where the energies cancel or they expand, and you're putting your laser through one of those nodes.
Simply stated, radar, near field, far field. Okay, what we're doing is we're having two near fields collide to each other. This is what's really acting on compression of the fabric of space.
Okay.
You take two near fields and you ram them together, you got some very interesting things that occur. However, you got to have the right geometry to do it. The reason why I used modified Koch curves was it was the practicality of the thing. I had originally thought I had two radio antennas and fly an airplane between it and then do linear displacement, throw a couple 100,000 watts of energy in an antenna and fly an airplane between the two antennas, because that's in essence what thunderstorms do when they cross fields and they form the warp tunnels and these airplanes fly through them. So the bottom line there was I had to figure out something practical, and I had been interested in fractals for a long time, but I read a paper from a guy at MIT who was a ham radio operator like me, and he was restricted on antenna displacements, couldn't build them in his apartment or hang them out the window. So what he did was he made a fractal antenna out of a coat hanger, and he fashioned it for the frequency that he was wanting to transmit on, and it worked great. So instead of having an 80-meter antenna where you'd have 90 feet of wire here and there, he had this fractal taped on his window and can communicate to ham radio operators all over the place. So he was a happy camper. He later started in a fractal antenna company and I don't know if he's still at MIT, but he started a fractal antenna company, and that's what's in your cell phone, little fractal antennas. Now, many of those antennas have the shape of a triangle, and they have multiple triangles embedded on top of each other, and that's what they use for the replacement of the pull-out antenna on your old cell phones. Now everything's compact. Well, the same gain can be had by a fractal antenna as a long wire antenna. In my case, with the iterations that we do onto the fractals, that's what makes it kind of like an Energizer bunny. It's the nested current loops that form because of the iterations on the fractals themselves. So we can compress and have as much gain as a normal antenna, but we have other features built into that indirectly, where you get two near fields colliding to each other. No one has ever done that before. How many radar sets do you ever see opposed to each other? You don't. How many antenna structures have you ever seen out in the world other than a corner reflector antenna? And they're just, they kind of bend a little bit and they direct an RF signal. But nobody does what we do on a near field, having colliding two near fields together in such a short distance. It works. I mean, you seen it pulling down on that was a 20 Newton scale. And with the weight of the object, and you saw the needle go up, it wasn't fantasy, it was reality.
Well, I mean, your output is just off the charts amazing. I'm just trying to figure out how everybody missed this for the last 100 years. I mean, it's like our stuff. You know, they missed it because it was so tiny, and they weren't looking for it. Your stuff seems amazingly huge.
I'm going to tell you, the only reason why I discovered it because I was a meteorologist by trade. Yeah, I teach physics and astronomy and all this other stuff, and I build boards and hardware, software, the whole bit. However, I've always been into cloud physics, and the pilot reports are the stimulus that got me to where I am right now. They reported these phenomena. I have reports back to World War II where tiger moth in northern London got caught up in a thunderstorm and got ejected downrange to the North Sea. He flew back, told the superiors, and they thought he was crazy. He wrote up a letter explaining the whole thing, and he left it for his family. And when the family saw us on television with this Bermuda Triangle business with Bruce Garnon and all that, they sent a copy of it, and it explained what had happened to him, which parallels Bruce Garnon's experience and several other pilots' experience as well. And the fact that what happened here is the cloud physics is the key. It's the crossing over of these intense thunderstorms, brute force power. You know, we're talking 10 to the 15th watts of power in these thunderstorms. These things are so dangerous. They make antimatter. They shoot gamma rays out.
So
what's that?
The thunderstorm is a DC thing. It's just a bunch of charge in a cloud.
Oh, no.
It's not a DC. Cloud. It's not DC.
And not DC.
It just goes up like that. It's not straight. It's not DC.
I see Curtis is with us too, so I just wanted to let you guys know Curtis is here finally.
Hey, Curtis.
Hey there.
And Curtis, do you have an update for us?
Well, Tim, hold on.
Maybe later. Let's let this.
We gotta let the meteorologist address the question about lightning.
Yeah. Let's continue. Thank you.
The bottom of the thunderstorm is 6 to 7 megahertz. As you go up through the thunderstorm to the top of the thunderstorm, it'll be in the gigahertz. In the freezing level range, it ranges from like 120 to 170 megahertz. You know, you pick a frequency, what you want. I've actually flown through these thunderstorms and measured the frequencies that we use that I mirrored the fractals to. But the secret in discovering what made these warp, non-sustainable warp bubbles for these aircraft is that the cross fields of these thunderstorms, when they flew into the tunnels in each of these cases, created the bubble that then ejected them out a linear displacement. I mean, Garnon went 100 miles in a second, less than a second. He went 360,000 miles an hour without the wings ripping off the airplane. And the other guys in Britain, the same thing. The other guys that went from Alaska to Japan is the same thing. Kwajalein to Guam, the same thing. These occur naturally. And I've done every job in weather possible, radar, upper air, and teaching it and the cloud physics of it, the interest in that. But the discovery of what made the linear displacement happen was the thing that I had to replicate here in the lab. And if it could do it in nature, you could certainly do it in the lab. Now,
Well, how does the cloud get to be megahertz? What's zipping about? Charge?
oh, it's all good.
I can explain. I can explain. If you have a ramp like that, it's a step, okay? Then you can basically use Fourier transform to basically that little area from here going up there, and it's a basically ramp up, okay? And you can convert that into frequencies because it's not a on and off. It's basically a step function has infinite number of frequencies, okay? But a ramp up function has a limited number of frequencies, and they have, because it starts from 0 and goes to something, and that time, okay, creates lots of frequencies.
Water vapor, as it rises in the atmosphere, cools down, and as you get into the freezing level, this is where the charge becomes active. Is the hydrogen, oxygen, the H2O, you give off a negative charge and you get a positive charge. And they literally climb up the sides of the clouds to the top and the bottom of the clouds. It's a dipole, plus, minus to the freezing level, minus, plus to the bottom. So you have a dipole on top, inverted dipole on the bottom, and you got the freezing level in between. And what the engine does is emulates the thunderstorm. The tripole fields are plus, minus, minus, plus. It's real simple. And the configuration of the fact that the V is similar to the crossing over of the fields of the thunderstorm. And like I said, the only way I figured this out of why these airplanes were being ejected out of the clouds like that was because of the cross fields that occurred. So in the lab, I had to come up with a mechanism to cross the fields with intensity. And one of the mechanisms that you could use to have great intensity and gain in a small restricted area was a fractal. And so everything that I've ever learned, everything I ever did came to solve the problem of recreating artificially how you can compress the fabric of space. Nature does it all the time. If you happen to be in the right place, the right time, it happens anywhere in the world. Doesn't make any difference. And that's what I found out. And in the same regard, electronically, you can reproduce and artificially create compression of the fabric of space with our particular design, our method of doing it. So that's where it came from, nature. I didn't invent this, compressing the fabric of space. Yeah, I invented the mechanism to artificially create it, but the mechanism was there. It was just, if you're a good observer, and that's what I do. I think I'm a good observer of nature and everything. I was able to take nature and put it back in the lab and artificially induce it. And it works. Despite all the, if you go to the internet, I don't even bother looking anything up anymore. I just keep working on my stuff. You go to the internet, you'll hear everything negative, blah, blah, blah. They ever build one? No. Have they ever gotten results? No. But I do, and I have. So don't care. I don't care what other people think. All I can say is we have results. It works, and we're working on refining this more and discovering all the intricacies of it.
Oh, I believe you. I mean, if you think you're alone and people ignoring you and saying that something ain't going to work, you're not. There's lots of teams out there that have stuff working, and everybody's saying no, it doesn't. I don't understand how clouds are generating RF.
Drew, I can
don't.
explain that to you. Okay, take
The ramp thing didn't explain it anything, dude.
no. Take the analog radio, okay, and flip a switch, and you can hear it. So that's that. Even if the voltage is DC, the thing going up for that time creates an RF, lots
Right.
of RF frequency, and you can
It's
test
pulse
it yourself.
DC. You're calling AC, but it's really pulse DC.
No, but if it's just one pulse, okay, you can hear for the time from the time 0 to the constant state. That creates lots of frequency, and if you can take a RF, basically the old radio, and you can flip a switch, you can hear that when you flip a switch.
Ham radio guys know all about lightning.
Well, I mean, I've set up a radio telescope and I've listened to the lightning on Jupiter. So, but
Yep.
that's DC. It's a whole bunch of charge rushing somewhere that there ain't no charge, and
You're actually just hearing static. You're hearing ionization.
Yeah. Yes.
But it's not DC. It's unbridled power. It's like thunderstorms. Thunderstorms ionize the air, and they can create and capture airplanes, surround them with a cloud of different colors. There's been pilot reports since Lindbergh and before him of being surrounded in a greenish cast, a gray cast, a yellow cast. Martin Caidin, a famous aviator book writer, got caught up in one of those things. There's been reports, numerous reports of it, and ionization of air, and the aircraft is made out of metal. And guess what? It forms a dipole. You can see up above it and down below it, but everything is encased. Can't see out the windows. It's
Are you describing St. Elmo's fire?
no, this is more than St. Elmo's. Of
Okay.
just dancing on the windshield, that kind of static electricity. Well, static electricity is unbridled. It's not DC or AC. It's just there. It's on.
Static electricity is charge.
It's charge.
It's DC. It's really
hold
not even.
up.
It's not flowing, so it's just static.
How about we give Curtis a chance to give us his update now, because I don't think he's got a whole lot of time available.
Yeah, Curtis, do you want to take it away, sir?
Sure. Actually, so I was uploading a slide, but I didn't get a chance to do that. So for this week, basically, it's been a while since I've been on here to give an update, but we're still working on getting funding for things. That's kind of moving slow, but that's okay. I have been working on the next experiment and getting that defined in terms of like what parts and pieces I'm going to get, what materials I'm using. That's in progress as well. So the plan is, for those familiar with Jim's work, there's the Mega Drive, and then there's also the Mach Lorentz thruster. So I'm actually going to be doing both, and primarily, more than likely, the first thing I'm going to be doing is the Mach Lorentz thruster. I know Michelle came and presented, and she's focusing on the Mega Drive for the most part. And then she has her own thing, the kitchen sink. But for me, the Mach Lorentz thruster is the next thing I do want to do. I'm excited about that one because I think we can probably up the force again if it all works out the way the calculations say. I am using the G4V based, the Carver-Mead based derivation of the Woodward effect now for most of my work, so that's good and helpful. But I'll try to put together a slideshow for next time where I can show you guys, what exactly I'm doing there. So that's the update for now.
Awesome. Thank you, Curtis. Thank you, sir. So yeah, we're rocking and rolling. This has been an enormous day. And again, so we've got in about an hour and a half, Denny will be coming on from Japan, and he's going to be showing us his repulsing replication. And so that goes back to Victor Schauenberger's work, right? World War I, World War II, I think.
And Curtis, do you have also an update on your theoretical work?
Sure. Well, I'm making good progress on the Brightwiller derivation. For those of you who aren't familiar with the Brightwiller process, that's basically the reverse of matter antimatter annihilation, where Brightwiller process is you get two gamma rays coming together and you get an electron and positron form. So that derivation, I've done it several times now. I think I have it figured out. I mean, doing these kind of things dynamically with PDEs, and especially this theory, which is more complex than GR. Yeah, and it's kind of a silly way of saying it because there's quaternionic numbers. But yeah, so that's going really well. I do end up with what I expected, which is a soliton that is of the form of the bicycle type Williamson van der Mark toroid for the way the field moves when the electron is formed. So what's also interesting is that tentatively that equation that I get when I solve it, I get three. Basically, I have a stable lepton, which is electron, and I get a metastable lepton, which is a muon, and then in higher energy there's a tau. But if I try to do a fourth generation, the fields actually start to overlap and don't form. You don't get the same shape. So that makes a lot of sense, and that kind of explains why there's three generations of leptons. I'm leaving I have a preliminary model, of course, for the proton in the theory, which is the scroll ring. And of course, the rest of the hadrons I'm pushing to a future work that's not going to be in the first paper. Okay, so if I did that, that would be like another year or something of work to get that done, probably. The other thing I am including as an update for the Rev 1 paper, which is out there now, is a calculation of the acceleration floor and the rotation curves of galaxies. That is not, so you can look up Machian Mond and you'll see like kind of like heuristic theoretical explanations trying to use Mach's principle to modify the effect of gravity, or that's what they call it. You could also call it inertia, whatever. But that particular phenomena is something that's very well measured. So it's not, you see that across a ton of different galaxies, the rotation curves at the outer limits. What that means is instead of like the rotation acceleration dropping with respect to 1/r, just like a Newtonian, you actually see an acceleration floor where you go out far enough, the acceleration of the disk doesn't go below a certain amount. Okay, so that's not expected. So that's the flat acceleration curve that is seen. And my theory predicts a flat acceleration curve. Now, I haven't calculated the numerical factor in front of it. It just gives like, okay, it is proportional to c times the Hubble constant. That's what I'm getting. Some proportionality constant should be derived. I've looked at different ways of deriving it. I'm right now of the opinion that for this first paper, I'm just going to say, okay, I get this approximately, and then I'm going to push that derivation along with the rest of cosmology, because I'm not trying to do cosmology in my paper. I can't ignore cosmology because my paper is a relational paper, which has to do with the rest of the universe. So I am doing some minimal assumptions about the universe. But I think with dark matter being basically not a thing, and there being an explanation of why we get the redshift and the rotation curves of galaxy, I think that's enough work for this first paper. It does strengthen it. And the main thing that's strengthened it, of course, is the Brett Willer derivation. So before Rev 1, I just assumed, okay, I'm taking the Wilson van der Mark bicycle kind of electron, and I called it a CAM electron, so I am treating it as a nonlinear stability using the CAM theory in nonlinear and dynamics. And that is strong enough, but with this derivation where I'm actually taking two gamma rays colliding in my theory, right? So one of the big problems was in Sachs's theory, he doesn't have free photons, right? So that was like, it took me a while to like figure out, okay, how am I gonna do this in this theory without, it's different than Sachs in that, he had the background pair gas assumption, so that's gone. So that was a big thing, and I've pretty much overcome that. And so that strengthens, I think that strengthens this paper quite a bit in terms of like getting lepton physics in there and having that be a solid thing where it's completely derived from the field theory. There's no importing anything, just like with the dark energy and everything else. And I'll say again, like in terms of Sachs's work, I mean, he spent his whole career, he produced there's a whole, basically a lifetime body of work there. The one thing, if you do look at his work, is that I've eliminated the background pair gas. So anything that he derives that depends on that background pair gas is not going to be carried over. But that being said, at the limit where matter is stable, some of his field equations will be carried over, right? So I can't assume the background pair gas, but when he treats a field side, and you can substitute the solitonic matter for that side. So when you're doing like astrophysics outside of stars, right, you can use Sachs's equations, for example, and things like that. So there will be a lot of things that we could use from Sachs, and some of the cosmology stuff he did derive will be useful. So just in terms of cosmology, because I know a lot of you are interested in that, Sachs's cosmology is cyclic. So he has a cyclic cosmology where the Hubble number is not a constant. It ends up being an equation that grows and shrinks. So that's a very useful thing. Now, I will say Rev 2 is going to include those. I do have a prediction for a current tension in cosmology that is unresolved, and I'm holding that prediction for Rev 3. So once I do Rev 2, the plan is to send that out, do a video, get feedback from physicists so that I can get some peer review before I send it to Foundations of Physics. So once Rev 2 comes back, I'm gonna fix anything I need to fix. Make Rev 3. I'm gonna add that prediction that addresses a current tension that's like well measured and recognized. And the measurement, by the way, it's getting better. There's some experiments coming up this year in the next 2-3 years or 4 years that will even get it more accurate. And so my number is different than the number that's commonly known out there for this tension. And so I've talked to a few people about it, but not too many. But I'm really excited because that's something I didn't have before until I realized that there is an active tension that I can like nail a prediction, and then later on this year, and then in the coming years we can see whether this was right. I think it'll be it'll make a big difference in terms of like acceptance out there for the theory. So that's basically putting me in a good spot in terms of like, I'm fortunate that these experiments are actually doing what they're doing, and this tension is going to be pretty soon resolved one way or another. So yeah, that's things are progressing. I just I have so many ovens, things in the oven, irons in the fire, that it just things are taking time. I have had some meetings with SSI as well, so I'm continuing to work with them and planning on doing that, and that's really great that they're supportive. So yeah, there's that theory work is going to continue, and like I said, I'm planning on with Rev 2 once it's done, doing a video, sending it out to like your guys, Joel, the Quisical group, and anyone that wants to participate. I'm not going to push it on anyone. A lot of people have their own theories that they're working on, and so I understand that they're like kind of invested in that, so that's okay. But yeah, I think this is a good spot, and I'm fortunate that I found that tension that's could like make a big difference in terms of acceptability of the theory.
Awesome. Yeah, I'm very looking forward to it. And Thomas has now brought his paper to Foundations of Physics as well. And we had a discussion about your theory, Heim theory, and like how we should continue about it. And we're gonna contact you again. He's like very busy at the moment, but we will reflect on the connections a little bit more in the next weeks. And we will build on it. And I think you're absolutely right. People are stuck in their own theoretical views and thinking. And I especially try to be someone who is doubling in multiple theoretical works at the same time, right? So my background is strong in Heim theory, but I'm like totally embracing what you're doing. I'm still looking at what people like Jack Zafati and Mohammed with his AI stuff are doing, or Maya Benowitz, for example, and other people. And what I do see is there are some common threads in all the theoretical buildings. And this is also what is showing here in the experiments, right? There is some patterns that come up throughout all the theoretical work and all the experimental novelties that are showing. And I think these are very strong connection points on which we have to bring also the theoretical landscape together. And David, this is also, I think, interesting for you, because there is actually some development on the theoretical end of the spectrum in the last months or maybe years. And we really do hope that we will be able to actually tell what is doing the effect. Why is the 70.53 degree angle the magical angle where it is happening? And how can you optimize for it? Also, you're saying to pulse drive your experiment is not really possible, but maybe there might be a certain frequency on which it actually works better. And so we hope that we can actually give this kind of detail by a theory that actually explains what is happening here.
I concur. Great points, Joel.
Yeah, so Joel, I think that's great. I think that one thing about it was like when I was developing UQFT, and it took, like, I think I told you this, it took me about a year to kind of get past the cognitive dissonance of solitonic matter. That just was really tough, like accepting that we're made out of light. So that was when you're trained that like, okay, matter is something different, and it's just that was really it took some time, even though I was like open listening. You listen to it, and if you go to the Quisical Group Society, go to the website, you can listen to Williamson's videos. They have so many videos on YouTube. It's great. And it's all explained, and it's great listening to John Williamson talk about QCD and his stories when he was at CERN, and like the paper, How to Tell QCD from a Hole in the Wall, and how it's just a bunch of parameter fitting, and really, I mean, he had the very similar critique to kind of the standard model that I do, which is like it's like the periodic table, which is great, it's useful. It's just not physics. It's like nuclear chemistry, you know. I'm sorry, but that's, you know, I was trained in the old school ways, I guess. I don't know. So, but yeah, it does take some time to get over like the things that you're like holding as, okay, this is what my understanding. And it's not always, and it's not always going to be possible for everyone, right? So that's just the way people are. So I know that's well documented by Thomas Kuhn and others. But I'm
Yes.
excited for the future because like right now we have a lot of computational ability, and so with this enhanced understanding, a lot of the why questions that are open, like, okay, why this, why that, why the other, a lot of those are answered. And so,
Yeah.
I mean, I think for me, the biggest one is like the thing that I didn't have to do. I did have to accept that, but I didn't have much of a problem with like not treating quantum as fundamental. I think that's the biggest thing that most people are going to have a problem with. They've been taught, and it's been like kind of beat into everybody's head that, okay, Einstein was wrong and quantum is fundamental, but it's insane because really, sure, quantum is right in its regime, but that doesn't mean it's fundamental. Say having something that, okay, everything is fundamental and everything has to engage with is a different statement than what we have experimentally, right? We don't have any proof that space-time needs to be quantized. That's just a hypothesis. That's like the easy way out. Like this whole thing about quantum gravity is okay, let's just quantize gravity now because we're quantizing everything, right? There's 50 quantizations in the standard model, so why not gravity? And it just doesn't work. And so, you know, and what's telling is like certain people, you know, the founders of the modern theories that we have pretty much didn't accept quantum as fundamental, right? So to find it as emergent from a nonlinear theory is kind of cathartic, right? If you're in that point of view. So, you know, I don't know how many times, like, you know, the guy at TOE, right, Kurt, posts all this, you know, he first posts like Toff and like Penrose saying quantum is wrong. It's like, okay, it's not wrong, but it's just not fundamental, right? It works in its regime, right? It's descriptive. It's a good descriptive theory that you can use for certain things, but it's not fundamental, is what the finding is. And most people are gonna have a hard time accepting that. They're gonna just not. It's gonna be really tough.
But the issue is that the quantum and stuff like that, all these things, okay? Like, I mean, I had a chat with a friend who just basically about psychic abilities and stuff like that. And he just made the face that, I mean, like I'm a believer. But I said to him, look, I'm an electrical engineer. And fields, what the hell is field? Nobody knows what it feels. But do I care? I have equations, I can solve it. That's what quantum theory is. You have equations, you solve, you predict, you make great predictions, but it tells you nothing how things really work. Absolutely nothing.
It's descriptive but not explanatory.
Yeah.
Completely. Yeah. And what's really great is that, you know, what we find, what Sachs did is he found that at a low energy linear limit from his theory, you get the formalism of quantum mechanics. You get the Dirac equation, basically. And if you looked at my paper, I get the Dirac-de Sitter equation, which is like, I was surprised, and I shouldn't have been. Like, just with like when I did the short-side solution, I got short-side-de Sitter. I feel like it's built in. Basically, it should have been. I should have expected it, but you know, that is a huge, big kind of like green flag in physics when you get a correspondence with a known body of theory, right? In this case, quantum mechanics is a low energy limit, and it works at low energies for stable matter. It really works. So that's all good. But yeah, I think that's going to be the toughest thing for most people. I think a lot of physicists are already accept like solitonic matter. You know, they're okay with that, but but having to drop quantum, right? You know, oh, when are you going to quantize this? You know, no, you're not going to quantize this. It breaks it. You know, it doesn't make sense. You don't need to. There's no reason why that would work. So,
but if you make the same predictions and then you use, you know, equations that go from here to here, this is something excellent.
Exactly. Yeah. Exactly. Yeah, and it's not. It goes from here to here, because it's conceptually understand, you know, but like the mathematics is not. It's not. It's just really rough.
And like you should think that physicists are very rational and objective people, but actually it's not true. There's a lot of emotion involved. There's a lot of groupthink within the system, and so there's a lot of bias. Which even if you show them a perfect mathematically sound derivation of something, if there's too strongly emotions against it, or too strong emotional attachment to the theory that they worked on for 20 or 30 years, then the person will not be able to look rational at the description. So there's a way to...
Yeah, even if they were just, I mean, it's a limitation of people that you get cognitive dissonance if you're like trying to look at something in this point of view you haven't ever before. We've all experienced it, right? You know, you can look it up if you know, for those that don't know what I'm saying. But yeah, it's like, it's going to be that for a lot of people. It's going to be, okay, I'm dropping. Okay, so one way to look at it is that if people go back and just like read what Einstein was trying to do, what he wanted for his unification, his wish list, the things that are in his wish list are exactly what I have. And that's what worked out. And I don't think any of us should be surprised. And by the way, one of the things, like, okay, so then why didn't he solve it? There's a big reason why, which is when he passed away, before we knew as a society, as a planet, we knew about parity symmetry violation, which is a fundamental, tells you what the fundamental symmetries of nature are. So without that knowledge, he wouldn't have, there's no way, unless he had guessed that and then did the unification and said, okay, I'm going to assume this symmetry is violated. Unless he did that, there was no way he would have figured this out. So
yeah, guys, I think we may, I may end up wanting to postpone Denny until next month, because we're kind of winding down for today. I think it might be best to close things down at 4. What are your thoughts on that? And that gives us about 10 more minutes.
Yeah, I agree.
I'm super excited to see his repulsing presentation. I'll see if I can get him to schedule a little earlier next time, because otherwise we're just kind of in limbo. And it's amazing conversation. I love you guys talking about this, but we've had some amazing presenters today. We've covered a lot of really great stuff, and I just don't want to like leave everybody kind of hanging, I guess, so to speak. So
yeah. Take a siesta for an hour.
Yeah.
By the way, on I put my paper on Zenodo. I've had over 550 downloads, which I'm shocked.
Do you want to put it up?
Maybe 100.
Curtis, do you want to share it? Share your paper. Do a screen share.
Oh, share. Oh, share the link. Okay, hold on. Let me.
Yeah. Yeah, just do a screen share and share the paper, and then
open that up, and then share screen. Window.
Let me see. Is this the unified quaternionic field, a covariant mechanism?
Yeah. There we go.
Okay, let me drop this into the comments too.
So yeah, that's the page for the paper. and I don't know who's downloading it. Maybe it's a bunch of bots. So that's quite a bit of people. So I don't know. The paper and
Someone's got some background noise going on.
It's probably
That's
me.
not me, but let me mute myself because
Sorry.
I'm typing.
so anyway, that's it. That's the paper. I don't think we have time to go through it, but yeah, let me. Oh, that's some other thing I was working on. Okay, let me stop sharing here. There we go. And find the tab where you guys are at. Okay. All right, I'm back. Anyway, but yeah, I'm really excited about getting that paper out. And of course, this whole theory was developed so that we could have a fully covariant mechanism for inertia that included, everything unified, right? So one thing is Hal had done a covariant, had done an update to Hoyle-Nolicar theory and actually derived the Woodward effect from it. So I've since done a couple other derivations of the Woodward effect, one using G4V from Carver-Mead and the other from Andre Aziz's force law, he has a relational theory that uses the force law of Weber, and I was able to derive the Woodward effect from that. So basically, we now have like several different theoretical frameworks that all derive the Woodward effect, as long as they're relational, and relational meaning they have the Mach effect as a fully expressed part of the theory, that you can derive a Woodward effect. So it makes the Woodward effect a lot stronger because previously Jim had only done it from Siama's Machian framework. So that was only one theoretical framework. But now we have, and then so Hal did Hoyle-Nolicar, then we had 2, and now we have 5. So we have mine, Carver-Mead's, Z's, the Z's paper, which I haven't released yet. I put that on Zenodo as well, and then the other 2. So that's, I think we have a strong foundation now.
Yeah. Now I would like to see the other side, right? So make the effect bigger by intelligently using the theory, right? So I'm really excited to see how the experimental program is going to develop in the next months.
Yeah,
or maybe the year. I don't know. You guys will need some funding, of course, to get that done, I guess. But yeah, that's going to be very fascinating. And I have to state again, since I found Heim's theory, this is the best theoretical work I have ever seen since I found Heim's theory. So and it is highly compatible with the ideas within Heim's theory, right? So I'm really excited about your UQFT work.
Yeah, thank you, Joel. I appreciate that.
Hey, Curtis. Is there any way any of the stuff you're working on is going to fix Jarod's graviflyer?
Yes. We can send it to space. Then it'll fly.
Sorry, man. Oh, that's it for me.
Well,
It's
and guys,
time,
I just, for my part,
I'm
I just
starving.
emailed Denny, and if he's watching or if he watches in replay, let me apologize to you. It was momentum. Having Mohammed, he had a prior appointment, so having like a 3-hour gap makes it kind of tough to keep things going and keep our momentum up, and it's not fair to you guys. So, but yeah, I would say today it was absolutely amazing. Absolutely amazing. I mean, I cannot stress enough, Jarod, thank you so much. Orestis kicked butt after you, and then I mean, David Perez and Reid Sherman, right? Like, so that was 4 amazing presentations today.
The 1-hour Q&A with David was such a treat. I've always wanted more Q&A time with him. It was so fun.
Yeah. And another thing that I'm doing on the alt propulsion site, I'm using AI, right? I'm very open about that. But what I'm putting transcripts from these presentations in. I'm trying to embed the presentations, at least most of the time, into the actual story. And I'm using a combination of papers and deep research along with the transcript to do more in-depth stories. And then it has links back to scientific information. And so I'm trying to do that for most, if not all of our presenters now, just depending on time. Oh, here, I'll put Curtis's up real quick.
So I just want to correct this because like when I gave my presentation in December, I had the wrong year for Jim. So he passed away last year. But I have this presentation that I did for CSUF, the colloquia. So I can if you want to schedule me, I do
for June. Yeah, I would love to.
Yeah, schedule me, and then I can give a presentation on the same as the colloquia and go over all those derivations that I talked about of Jim's effect, and hopefully I'll have like somewhat of an update of the lab, but I can at least show you guys where we ended up and what we have at the time. So
yeah, and could you send me a copy of that?
Sure.
Let me see. Mach's principle. I'll call it Mach's principle, inertia, and the Woodward effect.
Yep.
Yeah, and that'll be June. In fact, I could tell you what day it is now. I believe it's June 6th.
Okay.
Yeah, June 6th. Okay, and then I will see, and I'm crossing my fingers, but I'm hoping that Denny can do June 6th as well. And then Greg Cathcart actually has a new one. He's been doing a bunch of work on, he has been doing a bunch of work as well. So, and then by June 6th, hopefully we'll have more information from the U.S. government. Should I put that up? I should probably put that up. war.gov/UFO here. Just in case anyone in our audience has not seen it, which is probably nobody in our audience. This is the U.S. Department of War UFO page.
They're actually still the Department of Defense. They just call themselves the Department of War.
Yeah, because that's cooler. It's way cooler.
It's confusing if you're talking about the Dow, but which Dow are we talking about? The money one or the money one? I mean, war one.
So I thought this was interesting. And again, you guys will have to kind of surf around here and see. This is the surface of the moon. I don't know if you can see this effectively. The surface of the moon, and then in the air above the moon, you've got UFOs. And I don't know what that is. Well, they don't know what that is either.
I don't know about 10 to the -9 Tor being called air. Oh, what's that? Was that UFOs?
Those are UFOs taken by... So these are astronauts' photos. Apollo 17, 1972.
Who is bored enough to look at stuff like that? How did they ever find that?
The NASA people. They have incredibly boring jobs. They can surf through this stuff.
And the astronauts saw this stuff and were talking back to ground control like, hey, are you guys seeing this? So they knew to look for this stuff in the photos when they came back.
Now,
if you go to picture 5, you'll see a face. You'll see a face. The same face as you saw on Mars. You see? Area 5. Doesn't look like a face on Mars?
It looks like 3 dots.
I see one of those toys like it's the clown that you punch and it comes back.
So my understanding, I could be mistaken here, but my understanding is that the government is going to drip out a weekly update for the next forever, basically. And
cool.
And yeah, and Jarod, I think you told me about this. You said it was like a 40-week drip that they were going to do. It's going to be one batch per week.
If I had to guess, I would put my money on the timing of all of this leading up to the midterms, because why release something unless you can get some kind of leverage out of it, right? I mean, 2 for 1. So if they're going to release these, drip, 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 I don't know, 40 weeks puts us, into next year, but it would be interesting to watch the timing of the drips, because according to like Tim Burchett, he said, yeah, this is not, no, it's not nothing, but the oh crap moment is on its way with these drips. So
Also, there are 46, I don't know where I read this, there are 46 UAP videos that people have been screaming about. None of those were released yet. Supposedly those are coming up. So, but personally, so those moon images also, what they said is those have already been out there. Apparently those were leaked in the past or something, but this is official. So for whatever that counts for, I think that's interesting. Astronauts
Yeah, I
taking
think-
photos of UFOs. There were also a description of astronauts. They were describing UFOs around the capsule to ground control. But one thing that was confusing to me was the description initially seemed very straightforward, but then when I read it more, they talked about jagged objects, and I thought that could be a trick of light, but that doesn't sound like, it didn't sound like they were describing like flying saucers. So
Night, guys.
yeah, well, on that note, let me close things down. Gentlemen, it has been absolutely wonderful. I am so overjoyed to have all these presentations. Again, I'm going to update the Alt Propulsion site with these, and we have more amazing stuff coming up.
Thank you, Tim.
Night, everybody.